Thank you for thank you for joining. We'll get started in a couple of minutes. We'll let everybody else join as well. Good morning. All right, let's get started. So we are running behind a little bit in our course by almost half a lecture. So I'm going to have to speed things up a little bit from here. Uh, we'll still try and resolve all our uh, questions and queries in the same lecture. So I'm absolutely open to questions, but I'm just going to speed up things a little bit. So I'm going to pick up from where we left last time. And we had started talking about the structure of a robot, broad structure of a robot, and levels of autonomy, which we did not cover in the last lecture, but we're going to start talking about it today. Okay. So just to give you a recall of what we had discussed, we had left off discussing about mechanical joints. We spoke about how joints are a mechanism to connect two or more links together, right? So when we have rigid links, we use joints to connect them. And in doing so, joints essentially constrain the total degrees of freedom. So if I look at any rigid object, I have 6 degrees of freedom. However, as soon as I attach them with joints, I'm trying to limit the number of degrees of freedom in certain directions. And the resulting total number of joints for the entire system, the rigid links and the joint together, would be 6 minus n, where n is the number of constraints that have been imposed by the joint, by the presence of the joint, right? A simple mechanism would be a hinge joint, which takes two 6 degrees of freedom rigid links and constrains 5 degrees of freedom, giving you only one, right? Which is a rotational degree of freedom. We're also taking this example of a screw joint, which again takes two 6 degrees of freedom and makes one degree of freedom, which is again a translational, right? So whereas a hinge is a rotational, constrains it to one rotational degree, the screw joint makes it a translational degree of freedom. So this is what we had discussed in the last class. I'd asked you two questions. The first being, what is an example of a spherical joint in the human body? There are several examples. The most common and the largest joints which use spherical joints in the human body are the shoulder joint, right? This is a ball and socket joint, right? So very similar to a spherical joint, and the hip joint, right? So the joint at the hip is also a spherical joint. You may have seen videos of the hip joint being replaced and so on. These are all ball and socket joints, which are essentially spherical joints, providing 3 degrees of freedom. Okay. So the next question that I had asked was, I'd shown you this picture. Now, somebody had mentioned this is an universal joint. We'll see that this is essentially not an universal joint. This is a hook joint, very similar to this. Now, the only constraint here is we actually have constraints on this and this, right? So the only degrees of freedom you get are from the rotational pivot over here. You rotate about this axis. So you rotate about this pivot, that's 1 degree of freedom. And the second degree of freedom is about this pivot, which is like so, right? So you only get 2 degrees of freedom, one rotation as such, and one rotation about this pivot, which is like so, right? So this is an example of a hook joint. We'll see examples of a universal joint later on. Okay. So when using these joints, we have seen that there are two configurations that are possible, right? There's a serial and a parallel manipulator that can be formed with this. Now in serial manipulators, we had loosely defined serial monitors as all joints are actuated, right? So we see that there are actuators in every joint, right, typically. And these joints are connected serially, right? Sequentially with one another. And now we can define the degrees of freedom of this serial manipulator as the degree of freedom at the end effector, right? At the end of this serial manipulator is the sum of the individual DOFs, right? So if I sum up the individual DOFs provided at each joint, right? So in each joint, I only have 1 degree of freedom, all rotational, right? So if I add them up, I have 6 axes, right? Resulting in 6 degrees of freedom in total, right? So the Mhm. serial manipulator essentially provides you with 6 degrees of freedom. And you can calculate this very simply by adding up the individual degrees of freedom for each of these joints, right? And in this case, it provides only 1 degree of freedom per axis, right? And when you add them up at the end effector, at the end of this manipulator, what you get is 6 degrees of freedom in total, right? So now this is a more formal way of defining the degrees of freedom of a serial manipulator. For a parallel manipulator, it's a little bit more complicated, right? Now, you look at this parallel manipulator, this is an example of a parallel manipulator where you have different degrees of freedom for each joint, right? So you have different degrees of freedom for each joint. In this case, you had 1 degree of freedom for each of these joints, so it was much easier to add them up. What about this particular setup? So if you look at this parallel manipulator, if you look at it carefully, right, so there's a fixed platform, correct? Followed by a joint, which is 1 degree of freedom revolute joint, right? So you can only rotate around this axis, right? Around the central axis of this pivot. Then there is an unactuated joint, right? So this is an actuator, which is actuated and provides 1 degree of freedom. However, the second joint in the link is a spherical joint, right? So this is a spherical joint. We have already seen this joint in the previous lectures. This is a spherical joint, but this is not actuated. This is simply a joint. And this provides 3 degrees of freedom. Please review our previous lectures and see that a spherical joint provides 3 degrees of freedom. And then you have a hook joint, right? So we just discussed about a hook joint. This looks, if you maybe you can just zoom in a little bit and see that this is a hook joint. Okay, so this hook joint provides, yeah, so this hook joint provides an additional 2 degrees of freedom. So if you look at this, these three links make up a serial chain, right? Just like we had seen in the case of a robotic arm, these three form a serial chain if you just look at them in isolation. So the degrees of freedom at the end effector, which is this point, right? At the end of the hook joint would be a summation of 1 plus 3 plus 2, right? Providing you with 6 degrees of freedom at this point, okay? And for each of these arms, we have a similar configuration, right? All the 3 arms have a uh, uh, 2, 3, 1, except for this joint, right? So you look at it, there's a slightly different configuration. Maybe there is some specific need for it, right? So this joint, however, is not a spherical joint. This is again a hook joint. So for this arm alone, the total degrees of freedom would be 1 plus 2 plus 2, 5. Whereas the other arms provide 6 degrees of freedom, correct? So we have 2 arms providing 6 degrees of freedom, 1 arm providing 5 degrees of freedom, right? However, this is a parallel manipulator, which means there is only one end joint that is actuated, right? So, which is this platform, which is constraining the motion of all these joints together, right? So the total degrees of freedom that you will get over here is the minimum of the 3, right? So I have 6 here, and 5. So this end effector is constrained by the degrees of freedom of this particular arm, right? And since this arm is only 5 degrees of freedom, the end effector, which is this platform, will only have 5 degrees of freedom. It is losing 1 degree of freedom, even though the two other arms are still providing 6, right? So you will have, because these arms are connected to a rigid link. Hence, the constraints placed by the weakest link in some sense, or the link with the smallest number of DOFs, will essentially determine the DOF of the resultant end effector. Clear? So you can view these as serial manipulators, right? Calculate the total number of degrees of freedom in all of these arms, and then look at the connection and say that, okay, which one has the lowest, right? In this case, this arm has the lowest, consisting of 5 degrees of freedom. Hence, the manipulator or the end effector will only have 5 degrees of freedom and not 6 in this particular case. Had this arm been identical to the rest, we would have had 6 degrees of freedom. Okay, so this is how you would calculate the DOFs in a serial or a complex parallel manipulator. Okay, so now let's look at the different components in very broad terms that will be used to make a, uh, a robot. So we had seen this concept of sense, plan, and act, where there is a body, which is the body of the robot, right? And there's an environment and an external environment. Almost always, we are trying to manipulate some variables in the external environment. And this can be done only if we know what the external environment looks like. And this we do through several sensors. These sensors provide us with an understanding of the external environment and provide us with percepts of the environment, right? And these percepts are used to plan actions, and these actions then have to be translated into appropriate uh, environmental variables. which are done through this act stage, which is actually implemented through actuators, right? So in this scenario, we have three main components that are doing, which are executing the sense, plan, act model of cognitive robotics, which are the sensors, the mind or the controller, and the actuator. So these are the three critical components that we're going to look at in great details in coming lectures. Today, we just provide a bird's eye view. Okay. So first, let's look at actuators. Now, when we look at actuators, what do we really mean? So actuators are devices that drive links. They provide the power and ability to do work, right? And these can be of different types. We can have electrical motors, we have DC motors, we can have AC motors, right? So this is an example of a stepper motor, which you will very commonly find in many, many robotic applications. We are going to talk about the mechanisms of these motors in great details in coming lectures. Okay? So this is a DC motor, which is a stepper motor in this case. This is a geared DC motor, and this is a brushless DC motor. And each have their unique use cases, right? Apart from this, we also have AC motors. We have discussed that AC motors are typically used in larger settings, right? In industrial settings where you need to provide much higher amount of power, right? Then we have pneumatic actuators. Pneumatic actuators are typically used where uh, you can have essentially um, linear or translational motion, but you would want very, very robust action, right? But at the same time, they tend to be a lot slower than electrical actuators. Okay. Typical use cases that we have seen are these robotic arms, like Festo air arm, which we had seen in the previous lectures, right? We had seen how these actuators use air to essentially actuate different joints, right? Apart from this, we have hydraulic actuators. Please pardon the animation. This is supposed to be an AC motor. So hydraulic motors, one very common example of it would be in, in earth movers, right? And in many, many different industrial applications. Hydraulics are used when large amount of power is required, right? And in a typical system, you can have a combination of these actuators as well, right? You can have a combination of typically motors as well as hydraulics and pneumatics. A common example of this would be the modern robotic quadrupeds or bipeds that you see, right? Particularly the ones uh, 1 or 2 generations older. We had seen the example of the Boston Dynamics Bison, right, which was operating out of with the pneumatic actuators. But there were other joints that were controlled using the um, electrical actuators. And so you can have a combination of these actuators as well, depending on the needs of the particular joint, how much power you need from a particular joint, right? Now, so we said that actuators generate power. So this power has to be transferred to the links, right? And an essential mechanism of transferring this power, the power generated by an actuator, an electrical motor, or a pneumatic actuator, or a hydraulic actuator, and then transferring this to a rigid link, there is a mechanism in between these two. And you must have heard of this mechanism. These are called transmissions, right? One very common form of transmission is a gear, right? And the job of a gear is primarily, of course, to transfer power from actuators to loads or to joints and links. Okay. So they are used to transmit or couple the power from the source to the mechanisms that are going to actually deliver that force to the end effector, right? So that is the goal of a transmission. But there's another very important goal of transmissions. Transmissions are also used to transfer power at appropriate speeds. One example of this would be a gearbox of a car, right? So when you use the gearbox, you know that on the first gear, you're supposed to um, engage the first gear only for a certain speed of this uh, of the actuator, right? So when your engine is running at a certain RPM, when your car is running at a certain velocity, you engage the first gear. Then when it moves to a higher velocity, you engage the second gear. When it moves to the when you move to an even higher velocity, then you engage third, fourth, fifth gear. And why is this necessary? Because there is fundamentally a uh, trade-off between the amount of power that you can generate from an actuator and the speed with which it operates. What does this mean? That when I take a motor and I make it run very fast, let's say I take a DC motor and I make it run at 10,000 RPM, the amount of power I can get out of it, so amount of load I can act on it, right? If I put a 1 kilo load, it will stall, it will stop rotating. So the faster you go, the smaller amount of torque or smaller amount of power is available to you. Conversely, when you operate an actuator at a lower speed, you will get higher power, right? Now remember that uh, in a car, for example, you only have one actuator, which is the engine, right? And it is operating at different RPMs. So now, when the car is rotating or the wheels are rotating at a different speed, right? And you need different amounts of power. That's when you engage different gears in order to match the revolutions with the power required. So the gear provides you with this ability to transfer power at the right speed, right? So if you ask for too much power from a car at fifth gear, it will not be able to provide it unless you have the right gear engaged. Okay. Additionally, gears can also be used, transmissions, not just gears, transmissions in general. We'll see that gears are one example of transmissions. Transmissions can be used to change the orientation of the power as well, right? So one example could be, just let's look at this very complex mechanism, right? I mean, this is a made-up mechanism, of course. It was just meant to show you how many different kinds of transmissions you can have in a system, right? Starting from a very, very simple rack and pinion mechanism, right? In a rack and pinion mechanism, what happens? When there is a rotational motion in this joint, right? There is a translational motion. So this gear moves back and forth, right? So this is an example of a change in the conversion in the type of from a rotational to a translational degree of freedom. This we're going to come to later. But we were talking about transmissions being able to change the orientation of the power, right? So let's look at this straight bevel gear over here, right? So it consists of two gears with a certain degree of angle, right? You can find examples of this straight bevel gear over here. You can find similar examples over here. You can find examples over here, worm and wheel mechanisms. But fundamentally, what you can see is that these gears are used to change the direction. For example, in this straight bevel gear, as this bevel gear rotates along its axis, this gear, right, the smaller of the two gears, is going to change the direction, is also going to rotate, but it's also simultaneously changing the axis of rotation, right? It is providing you with the ability to change the direction of that force that is being applied or the torque that is being applied. Okay. Similarly, in this mechanism, in the worm wheel mechanism, the actuator, right, whichever direction it is is rotating this main gear in along its axis of rotation. When and as it rotates, this worm engages, which is a screw, right? And it changes the degree of changes the axis of rotation. Earlier, the force was being applied or the torque was being applied along the direction of this worm wheel. Now, the force will be applied along the direction of this worm, which is a 90-degree change in the orientation. Right? So this is one of the main, this is one of the biggest advantages of using transmissions. That even though your actuator is constraining the force or the direction in which you can apply the force, you can use a transmission mechanism in between to change that direction. And this is often required because you have complex mechanisms that are required, right? And then transmissions can also be used to convert rotary to linear or linear to rotary motion. We've already seen one example of this through the rack and pinion mechanism. Once again, this rack and pinion consist of two geared mechanisms. The first gear is a linear gear, right? So this rack has tooth, but on a linear platform, right? And this pinion has a mechanism which is similar to a normal gear that we are all used to seeing. As this pinion rotates, this rack transmits this energy in the linear direction, right? Back and forth. Okay. So this is simultaneously changing the direction of the force or the torque, right? Which is along the direction of the pinion, along the central axis of the pinion, towards the central axis of the rack. So that's mechanism one. But at the same time, it's also changing a rotary motion of the pinion to a linear translatory motion of the rack. Okay. So it's simultaneously serving two purposes. Okay. Now, there are much more complex mechanisms as well. And some of these you would have seen in your daily life, you would have seen in objects that you use every day, right? But the fundamental concept of a transmission is to transfer power at appropriate speed to change the orientation of this power, if necessary, not always, can be used to change the orientation of the power, or convert one type of motion to another, rotary to linear or linear to rotary. Now, some very, very common examples would be, of course, the gear is a very common mechanism, but another very common mechanism that you would commonly see is a chain and drive mechanism, a chain and drive mechanism, right? In this case, there are multiple links that make up a semi-rigid chain, right? So the change is conformable, it can change its shape, but it is made of rigid links. And this sprocket, right, allows you to transfer power from one actuator to another joint, right? And it's transmitting rotary to rotary. So it doesn't change the type of the mechanism, the motion, but it is able to transfer power from a sprocket to a drive mechanism, right? And these are, of course, very commonly seen in bicycles, right? So we're going to take one example of a bicycle, and I'm going to ask you what kind of mechanisms you see in it, right? Another very common example would be a belt drive system. Very, very common, right? This is present inside cars. This is present inside uh, agricultural machinery and many, many different applications for its simply because of its versatility, right? And of course, it is very similar in its mechanism to a chain mechanism. However, in this case, the chain mechanism is replaced by a belt, right? And in case of a belt, this could be made out of rubber, it could be made out of different materials, but this is not made out of a rigid structure, right? So this has a little bit of slack in it, right? Which has both advantages and disadvantages. So maybe you can think about what are the advantages of a chain drive mechanism over a belt and vice versa, right? But essentially, it performs the same function of transmitting rotary motion from its source to a load, right? From a rotary actuator to another joint, a rotary joint, right? And remember, This is allowing you to transfer this power at a certain distance, right? So the um, the actuated wheel and the joint that is being actuated can be situated far from each other, and this belt drive mechanism or the chain drive mechanism can help you move this power from one source to another. I see some questions. Let me see if I can. Yes, friction is in fact higher in cases of chain, but these are so that is one of the disadvantages of a chain. Think about the advantages of the chain as well, right? So more modern mechanisms are what exist, which combine the efficacy of a chain mechanism with a belt mechanism, and these are called strain wave gear mechanisms, very commonly used in today's humanoid and other quadruped robotic systems. These strain wave gear mechanisms have a very unique mechanism, right? So without going into too much details of how they work, let me just briefly explain to you what a strain wave gear mechanism does, right? Now we know that a gear is used to transfer power, right, from an actuator to a link or an actuator to another joint, right? So in this mechanism, what you do is let's say there's a central actuator, there's a motor, right, which is driving a cam. Right? So this green mechanism is a cam. And this cam is not a circular cam. This has an eccentricity. This is an ellipsoid. Okay? And what that does is it transfers power from the central cam to this gear mechanism, this chain wave gear. Okay? This red mechanism in between. Now, this red mechanism is simply a has gear tooth on it on its external surface, but it's not rigid. It is made out of a rubber material, right? It's slightly conformal, as you can see from here. So as the cam rotates, you can see that along with the cam, the inner tooth, right, which is also called this flex spine, is rot is engaging with the external tooth of shown in blue at different points in time, right? And this rotates. Right? So this rotation engages the flex spine with the outer circular spine, which is rigid. Once again, so you have an inner cam, which is eccentric, which has a slight bit of eccentricity from its from its ellipsoidal uh, shape. And this ellipsoidal shape allows the flex spine, which is made out of a flexible material, could be rubber, could be other steel mechanisms, very thin steel, which is flexible. And this allows the flex spine to deform along with the um, ellipsoidal cam. And when it deforms, it engages with the outer cam, as shown over here um, in this animation. So what happens? The power, right, from this inner spline gets transmitted to this flex spline, which engages with this outer spline at different points in time. And as it moves, this outer spline also starts rotating. But this rotation, the speed of this rotation and how much power is being generated from this rotation depends on the number of gears that are being engaged, right? And the speed at which this cam is rotating. Okay. So this allows us to transfer power from the inner spline to the outer spline. And we'll see one example of this here. Let me just, yeah. Okay. So as you can see, let me just pause the video over here to orient you. Yeah. So there is a Yes. So there is an inner spline, right, over here. So there's an inner spline over here, okay, which is this flexible mechanism, the flex spline. There is a mechanism inside which transfers power from this motor, which is a stepper motor. This is connected to a cam, right? This cam is slightly eccentric, which is not visible in this illustration. This engages with the inner spline, and then there is an outer spline, and we'll see that there's a gear mechanism in the outer spline as well. Yes, right? So this outer spline also has a gear tooth inside. Okay, so let's see how this engages. Okay, so just like you see in this video, right? As the inner spline rotates, the flex spline rotates with it, right? And this flex spline transfers this energy to the outer spline, right? And we'll see how this engages. Let's move forward. Yes. So as we rotate, right, certain parts of the gear will engage with other parts, right? And this will transfer the power to the outer spline. Notice that the inner spline is rotating at a higher velocity, while the outer engagement is at a much lower velocity. And we can see one example of this, you know, in the actual mechanism. So let me see whether the actual mechanism is shown over here. Yes, there it is. So here you can see the outer and inner mechanisms engaging with each other. You can see that there is a constant motion. And if you slow it down, what you will see is the inner mechanism is rotating much faster than this mechanism. So you can see that this will move one tooth at a time. Look at this red mark. Let me just go back 1 second. Right? So pay close attention to this red mark over here. Here. Okay. This is the rate at which the outer spline will rotate. So look at how much slower it is than the inner shaft, right? So this, what it is doing, as we said, that there is a trade-off between speed and power. So the inner shaft, because it rotates much faster, has much lower torque to offer. But as the outer shaft rotates much slower, it has much, much higher torque to offer. So it's trading off this gear, this strain wave gear, is trading off torque for speed or speed for torque, right? So it's giving you much higher torque, but at much lower speeds. So you can use a smaller, much lower powered actuator and transfer that power through the strain wave gear mechanism to get much higher torque. So you can use a weaker motor for applications where you need much, much higher torque. And this is now very commonly used in humanoid robotics, in joints where large torques are required. However, you only have small motors or small actuators that can be used because of size constraints or because of weight constraints. Okay, okay, I see some questions. What is the use of using an elliptical shape rather than a circular shape? So if this is circular, right, if this inner circle, if this inner cam is circular, it will not engage with the flex spline will not engage with the outer mechanism, right? If it's circular, all of the outer edges will always engage with the outer spline. So you will not get this slow motion, right? So if it's a circle, you will not get this slow motion. Imagine it is, because it's an ellipsoid, you can see this engagement rotating. If it's circular, you will not have the mechanism, right? Yeah. So this, yeah, you're right. In the video, the outer gear is stationary. You're absolutely right. That is because this is for illustration purposes only, right? So this is not meant to be a rotary motion. So what it's showing is that the outer mechanism, it can be held stationary, right? As you will see in the end of the video, right, he will actually show you that it is not stationary. See if I can, yeah, so in this mechanism, yes, right? So this outer mechanism is connected to this small cam that you see, which you're not actually able to see here. Okay. Okay. You're right. The outer mechanism is stationary. It is the flex spline that is actually transmitting. Okay. So these are some of the transmission mechanisms. And of course, we are just scratching the surface of what transmission mechanisms are possible, right? There are many, many different kinds of transmission mechanisms. I'm going to share this video. We want a deeper understanding of how strain wave gear mechanisms work. And of course, these are more advanced mechanisms. The simple mechanisms are what you will typically use in your daily settings, right? And in most cases, the simple mechanisms will suffice. So let's just look at some examples, right? The first is you can see in a KUKA robot, right? In a industrial automation arm, right? So we have seen these manipulators. Let's look at what is inside these, what are inside these robotic arms. So you can see in this case, that this is the drive shaft, right? So this is the arm that is being driven, and there is an actuator present over here, okay, right? And this actuator is producing, of course, the circular motion, the rotary motion, right? And this is being transferred through this belt mechanism. Now, notice what this belt mechanism is doing. This is not only transferring power to this cam, which will then rotate these joints, right? But at the same time, it's also changing the direction of the power. You see that the belt is actually rotating 90 degrees before it's making its way into the cam. Okay, so let's look at this mechanism once more, right? Okay. So as you can see over here, let me just replay this video. Lots and lots of mechanisms going on. Yeah. So if you look at this video very carefully, this belt is what is called a timing belt or toothed belt, right? So this is not a simple belt. This belt actually has tooth inside it, which allows the transmission to be used like a gear, right? So this belt is coming here, and then it's rotating this joint, right? And this joint allows it to be rotated at different speeds depending on the gear ratio, right? So the number of teeth that is engaging at different points. And very importantly, this allows the direction of the torque to be changed as well, right? So it changes from this direction to this linear direction, right? So the motor is actually rotating this particular joint. However, the transmission is happening at uh, this particular link or at this joint, right? So once again, please review this video very carefully. There are many, many mechanisms at play here. You will see the motor actually being driven from here. You will see that the belts are actually rotating this. There is a gear mechanism inside, which is then translating this force to the end effector, right? So at least 2 or 3 different kinds of mechanisms are present inside a simple joint like this. And the reason why you would use such a joint and a transmission mechanism is very simple, right? Notice that this allows us to keep the motor away from the joint, right? We can now place the motor away from the joint, at a certain distance from the joint, which means that the weight of this joint is transferred towards the base, right? Which means that the joint now itself is not as heavy as it needs to be. Therefore, I don't need to drive as much torque. So I can use the motor more effectively, right? So this is one of the reasons why you would use transmissions to transfer the weight from one position to another position. So you can keep your actuator, which is heavy, at a slightly different at a distance from your actuator, and then drive the mechanism from there. Right. So the only weight that the end effector is carrying is that of the gear, while the motor, which is a much larger weight, is sitting much closer to the base. Right. So this is particularly useful in a serial manipulator where each joint needs to have its own weight, its own actuator. Therefore, the weight can be distributed much more effectively. Okay. So of course, here you're using multiple mechanisms to achieve this. There's a belt mechanism. There's a there's a tooth gear mechanism, right? And there is a strain wave mechanism as well over here to amplify the torque uh, that is being achieved at the end effector. Okay. So similarly, we can have systems which are completely non-contact. Imagine somebody just mentioned that in cases of chain mechanisms, we have higher friction. What does it mean? It means that every time a tooth engages with the gear, you have some friction. You're losing some of the torque. What if we could have mechanisms that does not require any sort of contact to transfer power? Can we make non-contact transmissions? The answer is yes. We have different kinds of mechanisms, but one mechanism that is particularly very interesting is a magnetic drive system, right? So we'll look at an example of it. So if you look at it, there is a wheeled mechanism, there's a tooth mechanism here, just like a simple gear. And in each of these tooth, we have a small magnet. Okay? And then there is an outer gear, which also has tooth. And in each of these tooth, there is another magnet. Now, as this tooth rotates, the inner gear rotates, our goal is to transfer this power to the outer gear. Now, in order to transfer this power to the outer gear, in an ordinary mechanism, we would need contact between the inner and the outer gear. But since the inner and the outer gear in this case has magnets that are attached to them, we can transfer this force from this outer gear to the from this inner gear to the outer gear without actually making any form of contact, right? So we'll see that there's a small amount of air gap between the outer gear and the inner gear. However, since magnets, the magnetic field can couple through this air medium, we have the transmission of force from the inner gear to the outer gear. So let's look at one video of this. So as it rotates, we'll see that the inner and the outer gear actually never touch each other, right? So of course, the advantages are that there are no friction. This is one of the main reasons. And when you have friction, you also get noise because sound is one of the ways in which through which you have dissipation of power. So there is no noise because of no friction. And because these gears are not physically engaging with each other, there's also less vibrations, right? But can somebody tell me what is the disadvantage of such a gear system, of a non-contact gear system? You can unmute and tell me if you want.
Low power transmission.
Yes, that is absolutely right. So, as you know, magnetic field, as you go further away from the magnet source, the more magnetic energy or the magnetic power you're going to lose, which means that whenever you have a small amount of gap, you're actually losing power, right? Unless the magnet is extremely powerful. Of course, if the magnet is powerful, you will need a larger magnet, which means you're going to increase the weight. So this transmission of power, although it's frictionless, but you are losing power simply because of that air gap, right? And there is another aspect to this when magnets also get heated up when they are in circular motion, right? So when two magnets rotate about each other, they're also going to create currents inside these magnets, which will heat up this coil. It is almost going to act like a electromagnetic generator, right? So there is going to be heat in the system as well. But that is a minor problem. The bigger problem is that because of this air gap, you're going to start losing some of the power. So it is not as efficient as it looks. Of course, there is very little friction, but you're also losing power because of that air gap. So the air gap is both a blessing and a curse in disguise. Okay. All right. So let me just look at the chat and see that there is, yes, low torque. Yes, backlash is also there. That's also a very good point. So what is backlash? Can anybody tell me what backlash is? So Adam says that there is no backlash.
Polanski,
I'm sorry?
Polanski, uh, explain the backlash.
Yeah, so backlash is a very interesting concept, right? So backlash is very hard to explain without actually having a, let me see if I can explain backlash. Let's try with the stream, not with the stream wave, maybe over here. So if you notice, right, in an ideal gear, right, the inner and the outer gear, as you see, are engaging perfectly with each other, right? So there's an inner gear, there's an outer gear. They have exact same dimensions and they engage with each other. But in real life, that sort of engagement is not possible because you cannot make two systems that are perfectly, of course, they don't have perfect alignment. There's one problem. They're also not going to be of the perfect shape. And if you make them of the perfect shape, they're not going to engage very effectively either because they're going to jam up. There's going to be all sorts of problems. The friction is going to increase and so on. So as a result, when you make this inner and outer gear, you will have to leave some space in between. So the inner and the outer gear dimensions are not going to be exactly the same, right? Which means that in a gear, when you start engaging, there's going to be a zone where before which you will not see any motion. So as you rotate the inner gear, because of this imperfection in its, or because of the construction and the imperfection in its design, which is again necessary, you're going to get a small amount of movement or small amount of movement in the actuated system, which will not transfer over to the secondary gear, right? So if I have imperfect contact over here, I will have some motion which will get wasted before I start moving the outer gear. So this is called backlash. And this backlash can also be present in any, so it's present in contact based gears. It will also be present in these gears as well, right? So if you look at it, because these magnets, are not perfectly aligned, perhaps you will get some motion of the inner gear where you will not get any motion of the outer gear. It is possible, right? Now we cannot.
Can I say
We
something?
yes,
Sorry.
yes, please go ahead. Yeah,
So if I have to simplify it, I'm just asking whether I'm right or wrong.
yeah,
Let's say we are pushing a load. If
yes,
we are pushing a load, at first our foot may slip until unless we get a proper friction to push that load. Is that slip
correct.
the backlash?
That is part of backlash, but not the
Okay.
only mechanism of backlash. So backlash is
Okay.
necessary. Backlash, without backlash, gear systems will not work. Okay.
Okay.
That is the first thing, that you will
Mm,
need backlash for gear systems to work. So if you think of it, if I'm having two gears and they engage perfectly, in an ideal world, they would transmit power absolutely perfectly. But in
mm,
a real world, it will actually lead to jamming, right? So it will
mm, mm, mm,
actually sort of jam the gears. So the two systems that are at play is that there is friction, which will prevent the joints from moving till a certain amount of static friction is being overcome. That is one. The second is because I cannot make these gears perfectly align with each other or perfectly
mm,
uh, engage with each other, I have to make them the inner gear to be slightly smaller than the outer gear, right?
mm,
Which means that if when I engage them, there's going to be a little bit of movement between them before that movement is transmitted to the outer gear, right? So there is a little bit of play in between the inner gear and the outer gear, which is necessary, without which it will not work. Which also means that there will be a little bit of jitter before you actually start transmitting that power onto the outer gear, right? So it is
Got
a
it.
combination of the static forces that are preventing that gear from engaging, and and it's also coupled by the fact that the gears have imprecise construction by design, which is necessary for it to not get jammed. And this imprecision actually gives rise to a little bit of wasted movement. And that is called backlash.
Got it. Thank you.
Yeah.
Thank you.
Thank you. All right. So
Can I
moving
have a
on.
question, please?
Yes, please go ahead.
Yes, when it moves or it operates, even if it is a perfection, due to the time, the tools may get corroded away or eroded away, and that can also create backlash. Is what
Yes.
generally I've seen.
Yes, of course. So in a gear which is imperfect, even an imperfect gear will get corroded over time because there's friction. No matter what you do, friction will lead to heating, and this heating will lead to corrosion, right? So corrosion you can't prevent, whether it's imperfect or it's perfect. But in a perfect system, what has happened is the frictional forces will be so large that the gear will end up wasting a lot of power trying to overcome this friction in order to move. So imagine two surfaces making perfect contact, right? Perfect meaning perfect contact, right? There's no space in between them, which
Correct.
means
Correct.
that first of all, that contact has to be overcome. That contact friction has to be overcome in order to start moving, right? So
Right.
that friction itself will be a wastage of power. So we make it slightly smaller than the inner and the outer gear, slightly imperfect.
Correct.
But even then, you are going to have engagement, and you're absolutely right. Over time, this engagement will lead to friction, losses, and the backlash will increase over time, right? The backlash is
Yes.
not static. Absolutely
Yes.
right about that. Yes.
Thank you.
Thank you very much. Okay, so your task for today when you go home is to uh, start looking at the mechanisms that are used in a bicycle. We have all seen or have bicycles at home. Some of us have may have seen these gear mechanisms, right? So you have to identify, go through videos of gear mechanisms of a bike and identify the major transmission mechanisms. What are the different transmission? And there's more than one. Please remember, of course, the main mechanism is a chain drive, but there are other mechanisms at play as well, right? So if you look at how the different gears are engaged from 1, 2, 3, 4, 5, 6, try and identify what are the actuation mechanisms involved, what are the different mechanisms involved, right? And then try to understand whether we should use a lower gear, that is a smaller sprocket, or a larger sprocket when I'm trying to go over uphill, right? So if I have a geared bicycle, and many of you may have, uh, you know, actually used geared bicycle. So when I have a geared bicycle, which gear should I use when I should go uphill? A smaller gear or a larger gear? And try to reason this out in terms of torque and power. In terms of torque, power, and speed, rather. Okay. So please try and answer this for yourself. The answer is actually a one-line answer. Plus, please reason, right? Why you need a smaller gear or a larger gear in order to go uphill. And the assumption here is that as a human being, you don't want to use up too much energy, right? Your energy consumption is limited. So therefore, if your energy consumption is limited, the amount of power that you can transfer to the wheels of the bicycle is limited. How can you maximize the efficiency of the system by using this gear mechanism, and which gear you should engage? Okay, all right. So now we have spoken about actuators. We've spoken about how transmissions can be used to transfer power from actuators effectively to the environment. Last piece of the puzzle is the sensor and the mind, right? We're going to just briefly provide an overview. We're just seeing the overview of a robotic system, and then we're going to move on. So when we talk about sensors in robotics, of course, there are different kinds of sensors depending on the applications. But there are two broad categories of sensing systems that we use, right? The most obvious way of looking at sensors is to understand the external environment, right? So when I, as a human being, want to look at this world, I'm using my eyes to sense the environment outside. When I have a cup and I want to know how hot it is before picking it up, I use the receptors on the surface of my skin to touch and feel the object, to understand whether it's light, whether it's heavy, to understand whether it's safe for picking up, whether it's hot or it's cold, right? So these sort of sensors are called exteroceptive sensing because it's external, right? And as we all know, there are many, many examples of it. There are vision systems that are used in different kinds of autonomous vehicles. There's an example of a Tesla LiDAR system along with a camera that is trying to identify the kinds of objects that are present, the kind of vehicles that are present, the signals that are present, right? Which is green, which is red, which directions are available. This can be used for path planning. It's very similar to our vision systems. This is also present in less sophisticated systems, not as sophisticated as autonomous vehicles. You can see this in a robotic cleaner, right? So here is an example of a Xiaomi cleaner. So this is a fully automated robotic vacuum cleaner. Now, as you will see, as the light is turned on, the mechanism that is used to sense the external environment, which is a LiDAR system, right? So let's see when the light turns off. Let me move ahead. There it is. Okay. So when the light is turned off and we look at it through an IR sensor, right? IR, you see these rays of light that are bouncing off the walls, right? So this system is called a LiDAR. We're going to look at this in details later on. Essentially, it's shining a laser and trying to find out where the different walls and the different obstacles are present, right? And this is also an example of an exteroceptive sensor because it's looking at the outer environment, mapping its environment in order to provide some sort of idea of where to navigate and where to do how to plan the path for cleaning operation, right? So one of the main goals of exteroceptive sensing is to just make sense of the environment. But at the same time, this can also be used, particularly in human-robot collaboration environments, to protect the user. So here is an example. Let's just pause. Okay. So here is an example of a user and a robot collaborating to a single task. The robot has some task that is assigned to it, the robotic arm in particular, and the human exists in the workspace of the robot. So it is absolutely essential for the robot to avoid the human and any collision with the human. Excuse me. So any collision with the human, right? And in order to do so, we need some form of a sensor to sense where the human is with respect to the robot. In this case, there's a camera system, right? Which is looking at the entire workspace and figuring out the location of the human and providing trajectories to the providing work envelopes to this robot, which are safe. So as you just saw, when the human came into this work envelope, automatically the path planning algorithm shifted its path or changed its path to make it safer and avoid collision with the user, right? So this exteroceptive sensor can be used to protect the user. It can also be used to protect the robot. For example, again, we're going to look at the example of a robotic cleaner. Now, of course, this cleaner, robotic cleaning system, if it goes down these stairs, it's going to damage itself. So it needs to have a stair avoidance or an avoidance system that looks at this cliff, almost like a cliff avoidance or a stair avoidance system, and protect itself, right? So it must protect the user, but it also has the ability to protect itself. Okay, so let's look at how that does. And in some of your projects, you're going to do this exact mechanism. We have projects that will help you understand these protection mechanisms extensively, right? So it's simultaneously cleaning and also avoiding that cliff in order to make sure that it doesn't fall through. So it's mapping the environment, it's protecting the user, it's protecting itself. But there is a third task, which is to ensure that it's able to manipulate external objects to make changes in the environment. And as it's making changes in the environment, to be able to sense what changes it has made. Okay? So manipulation of the external environment, for that, sensors are absolutely necessary. So here you see a robotic arm with these small tactile sensors called BioTac. This company doesn't exist anymore. However, this was a company out of University of Southern California, which was one of the first companies to make tactile sensors. These tactile sensors, once they interact with objects, they produce electrical changes, right? So they'll produce electrical signals which are directly proportional to the amount of pressure you have applied on the object. And this allows the object to be picked up effectively, right? We'll see that it's able to pluck these grapes, which if it did not have the sense of extroceptive sense, it would not have been able to pick this up effectively without crushing them, right? So these sensors are helping manipulate the object safely, right? We'll also see one more example. This may not be as clear as the other one. However, in this case, the actuator, the linear actuator that you will see over here, will press on a ball, right? And it's designed in such a way that, let's see if we can show this video. Yes. Yes. So it can squish on a ball, but at the same time, if it's squishing on a rigid body, too much force can lead to, of course, it can crush the object, but it can also lead to damage of the system itself. So as it's manipulating the external environment, it can also be used to protect the robot itself from harm, right? So again, very similar to the previous example that we saw. All right. Now, apart from this, if you look at our human body and take this as an inspiration, while we sense the internal environment, we also know exactly what is going on inside our body. And this sense is called an interoceptive sense, sensing the internal environment. One very common example of this, if you look at our human body, is that I can close my eyes and I know exactly where my finger is, right? So I can close my hand and I can touch this other finger with my finger. This is despite my ability to see, right? So even without my ability to see, I'm able to touch the other finger, right? I'm able to touch different body parts, right? Without the need for seeing it, which means that there is some internal sense within my joints, within my muscles, that is telling the body exactly where the body is in space. And this is called the sense of proprioception. In case of the human body, this is called the sense of proprioception. Proprioception is our internal sense of what the individual joints, individual muscles of the body are doing. And this allows us to keep a body schema or a body image. This is very useful because if I don't know where my hand is in space, I will not know how much to move it when the need comes. Similarly, robots have a ability to measure its internal state through interoceptive sensors because it is absolutely essential for it to know where it is in space, right? So if I've asked it to move to a coordinate, whether it has actually moved to that coordinate or not is decided by the ability to measure how much each joint has moved, right? So let's look at, again, another video where the repeatability of a particular robotic arm is being tested. So robotic arm is being asked to go to a certain position every time, the same positions every time, And through a micrometer, we are measuring the different distances that it will measure. So you will see that every time it goes there, there's slight variation. 3.88, 3.93, 3.93, and so on and so forth. But it's able to go there precisely every time because it knows exactly how much each joint has moved. Of course, there are errors in the movement of this joint, which is why you see this changes in the different mechanisms. So there are internal mechanisms that are present, right? Similarly, it can also be used to protect the robot or the user from collision avoidance, right? So the interoceptive sense can be used to avoid any sort of collision. Let's see how this works. Okay. So you will see a robotic arm, right? And this robotic arm, once it makes contact with any object, it's automatically designed not to exert any more force. How is this working? This is working because each of these motors inside these joints, right, have a certain amount of current that they will draw. So for any motor to move, it requires a certain amount of current. When you're pushing against this motor, when an obstacle exists and you're pushing against this motor, this current increases. So if you are able to measure the amount of current that is going into the motor to drive it, and you see a sudden spike in this current, you will know that there is an external entity that you have actually collided with. So this is a way of understanding whether you have made collisions or made contact with an external body simply by measuring the internal state of the robot, right? So you do not have any external sensors. You only have internal sensors, which you're using to estimate whether there is any external entity that you've collided with. So this is again an internal mechanism that is helping understand whether an external environment has changed or not. And there are many, many mechanisms that can be used to do such change. Of course, we just spoke about how the current can be sensed in a motor. But very simply, you are going to also look at servo motors, right, later on. And in your projects as well, you'll have servo motors. So in a servo motor, there is a small specialized sensor, right? So there's a small specialized sensor called the potentiometer. Again, we're going to come back to these in details, which measures how much this motor has rotated, providing it the ability to regulate this position carefully. So if I ask this motor to go to 10 degrees or 20 degrees or 30 degrees, this potentiometer will help it understand whether it has actually reached that state or not and adjust its error accordingly and make its error zero over time. So this is an example of an actuator which has an interoceptive sensor inside to understand its internal environment. Okay. Any questions till this point? Yes, Agnishekar, please go ahead.
This is what we have seen is that when it touches a particular or when it has some obstacle, it comes back. Can we use some sort of a proximeter with a given distance, saying that if it goes beyond that, if it senses something beyond 5 mm or 6 mm, it should come back? Can we do something like that with a proximeter?
Yes, so
Sensor?
yes, you can do it with a proximity sensor. There are also something called limit switches, right, which are used.
Yes, yes.
So this is commonly used in 3D printers, and I have a specific slide on limit switches as well. So when we talk about the different mechanisms, extroceptive and interoceptive, when we go towards the sensing and actuation module, we're going to talk about these in details. Yes, you can use optical methods, you can use contact-based methods like limit switches. There are many ultrasonic methods of sensing whether you've crossed a certain barrier or not. And yes, they provide different kinds of mechanisms, so they will help you constrain the workspace of the robot. It can help you set what are called restricted workspaces to protect the user sometimes, particularly in human robot collaboration. Yes, you can use all of this. Yes.
Thank you. Thank you for the clarification.
Thanks a lot. Yes. Any other? Yes. So Adam mentioned increase in amp. Amp is amperage, which is corresponding to the increase in the current of the program. That's absolutely correct. All right. So at this point, I would like to take a small break, and then after we come back, we are going to talk about the last section of the Sense Plan Act module. This is setting up. Yeah. So we're going to talk about the last bit of the Sense Plan Act module, and then we're going to move towards levels of autonomy. Okay. So we'll take a short break of 5 minutes. It's 11:15. So we're going to come back at 11:20 and then continue our conversation. Okay. Thank you so much. We'll be back at 11:20. Thank you. All right. So while you were away, I was looking at some of the questions and some very interesting questions. So Swadesh asked two very good questions. Let me just quickly answer them before moving on. So the first question is, when we add up all the DOFs, could we reach an arrangement where we have more than 6 DOFs? And if so, what does it exactly mean in a spatial arrangement, since 6 DOFs are what we would need um, to have positional, translational, as well as maximum rotational degrees of freedom in space. You're absolutely right. You could have more than 6 DOFs, but anything more than 6 DOFs is a redundant system, right? So, and we'll come back to it later on when we talk about the importance of redundancy. Uh, so if you look at our human body, right, and you add up the total number of joints, for example, of our hands, right? So this is a great exercise. So add up the total number of DOFs in all our joints. It will add up to much more than 6. Okay. And the hand actually has 21 degrees of freedom. Okay. So you would wonder, why do we need 21 degrees of freedom? The answer is that redundancy allows you to perform functions that are typically very, very difficult if you have only 6 degrees of freedom. For example, our hand, when you have pain in one part of your joint, or let's say one of your muscles are fatigued, right? You can still perform the action because you have other muscles or other actuators, so to say, that can take up the responsibility of that particular joint. So this redundant joints can be used almost as a fail-safe mechanism, almost as a mechanism that provides you with additional options or multiple ways of doing the same operation. So I can, if I have an object here, I can reach it via a straight line. I can also reach it via a curved line. I can also reach it via from the opposite end. And this is possible. I have these options because I have multiple degrees of freedom, more than 6 degrees of freedom. And let's say if the straight line option, straight line path option is not available to me due to some malfunction of some particular degrees of freedom, uh, I could then substitute this for other actuators, right? So that's the role of redundancy, to provide fail-safe mechanisms. And our body is an incredible example of a highly redundant and highly robust system. So redundancy leads to robustness, right? So that is one of the reasons why you could have a system that is higher than 6 DOFs. And yes, the system will have DOFs more than 6. You would count the DOFs, and you will not say that, oh, well, I don't need more than 6. So even if I add up more than 6, it doesn't matter. No, a 7 degrees of freedom arm is absolutely possible. And in that case, anything apart from the 6 degrees of freedom is a redundant system, right? It would not bring you any additional advantages other than redundancy. Okay. So the second question is, the certain joints in parallel setup with no actuators, what is the benefit of having non-actuated joints? Well, in non-actuated joints, as you saw, joints are essentially used to change the direction of the force, right? Or the type of the force, right? So if you have a rotary motion and you need to convert this to a linear motion, and even in case of a serial or parallel manipulator, that is what it's serving. It is changing the direction in which the force can be applied from a simple rotary to a complete 3 degrees. So, for example, a spherical joint has 3 degrees of freedom, right? So this 3 degrees of freedom is being obtained from from a rotary motion, right? So this allows some, again, increasing the degrees of freedom that are available with the joints, or decreasing it depending on your application, right? So with that, I'm going to start continuing. I think there's some question about IPL. Sorry, I don't watch IPL as well. So yes, if it's a quadruped RoboDog, which has 12 degrees of freedom, I guess. Yeah. I'll have to get back to you after watching one match at least. All right. Okay. Uh, okay. So we spoke about interoceptive sensing. Now let's move on to the heart of all of this, right? So we have a bunch of sensors, we have a bunch of actuators which are either sensing or actuating within the body or the environment. But to make sense of all of this, you need a controller or a system that can assimilate the sensed information and then develop a plan which then translates into action, right? Of course, in our robotic systems, we call this as a controller and not a mind. So here is a very basic example that I took from a paper, and I'll link the paper. Very basic example of what a system might look like, which has multiple sensors and actuator modules, right? So this could be for example, a mobile robot, it could be a quadruped, a biped, right? Anything. So in general, you have an environment which has obstacles. It could be a simulated environment, for example, a maze that you're trying to solve. So it could be mock-ups. There could be a command module which allows the user access through a joystick or through an external command module, like in a CNC machine, there is a command center, which provides movement commands, right? This could be pre-programmed commands, or this could be a set of instructions to allow the system to understand what its external task is. And then, of course, you have your battery, power supply, and so on. Now, within the robot, of course, you have your cameras, your LiDAR systems, there could be potentiometers, there could be encoders, a bunch of host of systems that are part of the sensing module. Now, these sensors are then, the outputs of these sensors are made suitable so that a computing platform can understand it. In many cases, these data will be in the form of in digital format in a camera. This could be simply a parallel interface. We'll see how the Raspberry Pi camera works later on. So this could be in a parallel interface. A 2D LiDAR could be a point cloud. You can have encoder data that is, again, analog or digital, but it has to be made suitable such that the computing platform can understand this. And once this is inside the computing platform, different mechanisms can happen, right? Of course, we could have different machine learning algorithms that could make sense of the camera data. So YOLO is a model that is used widely for object recognition. What kind of objects? What is the object? Where is it located? Right. So this sort of intelligence can come out of machine learning algorithms, even traditional algorithms for that matter. So this is an example where a camera data is being passed to a YOLO model, a deep learning model, which provides some understanding of what the object is that is present in front and where does it spatially in space. Additionally, a 2D LiDAR system, a LiDAR system which tells you in 2D where different obstacles are placed, you get a point cloud out of it. And from this point cloud, again, you can find out where the obstacles are, where, not what. Okay. And of course, these two systems are providing somewhat complementary information that are similar but not the same, right? So when you have similar systems, they will provide data in slightly different formats. So you have to make sense of both of these data in unison. So we use what are called sensor fusion algorithms to try and make sense of what the camera is seeing together with what the LiDAR is seeing, right? In order to give us a better sense of the world. Again, this is closely related to the concept of redundancy, right? So when you have multiple systems looking at the same environment, you get information that is complementary to one another, similar, but also there are certain aspects of it that are complementary to each other. And this provides you with robust output from the sensor fusion process that can help you understand where the obstacles are in its place, what is the path that has to be planned, and so on and so forth, right? Apart from this, of course, you also need to make sense of the trajectories that are going to be executed, how much a wheeled robot has to move, and then execute that through some form of actuation mechanism, right? So maybe in this case, these are wheels. So all of these sub-functions will be part of the main control system, right? Calculation of the or computation of the deep learning architecture. Then there's LiDAR data processing, sensor fusion algorithms, the different kinds of sensor fusion algorithms, SLAM, VSLAM. There is, Kalman filtering, which can make sense of IMU data and so on and so forth. So all of these are running on either an embedded or some form of computing platform, right? While at the same time acquiring data from the camera system and driving the wheels of the robot or the actuation system. Right? So this is what the brain of the robot will broadly look like. We'll look at it in much more details in coming lectures when we talk about different kinds of computational platform. What are the computational challenges that are involved with this? So broadly, this is what the brain of a robot would be, which completes our sense, plan, act model of our robot, right? So with this, now we start looking at levels of autonomy. So when we talk about sense, plan, act, how much of these functions need to be performed by the user, and how much of it can be offloaded to the robot itself? And this sharing of function, the sharing of control, is what gives rise to autonomy, right? And there are different levels to which this autonomous systems can be built. So we are going to try and see how can we define and differentiate autonomy from automatic systems, autonomous systems versus automatic systems. How we can systematically define the appropriate level of autonomy for a particular system that we're defining. Can we build a framework towards it? And finally, we are going to discuss what are the ethical boundaries that we must consider through some anecdotes. Okay. All right. So when we look at levels of autonomy, let's look at 3 particular examples. Okay. So the first example is that of adaptive cruise control. So many of you may have cars that have cruise control built inside these vehicles. What is cruise control? Cruise control is you ask the car to maintain a certain speed on the highway or on this road, and it does so, right? So if you've set this cruise control to 50 kilometers per hour, it's going to maintain that speed no matter what happens, right? Until you intervene, press on the brakes, and the cruise control disengages. Adaptive cruise control is one level higher than this. Okay? In adaptive cruise control, we have the option of giving the car the velocity at which we want it to drive. But additionally, we can also tell it, look, there is a car in front. Maybe this will not work as well in India. But if there is a lane and there is a car in front, slow down when the car in front of me slows down automatically. And perhaps speed up, but don't reach the speed limit of 50 kilometers per hour. Okay? Thereby trying to maintain a fixed distance from a certain target. Okay? So let's look at how this adaptive cruise control works. So there would be certain sensors that would try to capture through a radar system or certain systems, what is the distance between the next car and itself, right? So when the other car slows down, this radar is going to pick it up as the distance shortening, right? And it's going to automatically slow itself down in order to maintain a fixed distance, which is not something that a regular cruise control car is going to do. As you saw, as the distance increased, this car sped up in order to maintain a fixed distance between the two. Okay. So this is an example of an adaptive cruise control system. And this is available in several cars now within India as well. I don't know how much useful it will be in India, given the traffic situation that we have, but these are available. On the other hand, we can have a system that is fully controlled by a human, right? So this is an electric wheelchair, right? We're just going to look at the mechanism. So of course, this is a joystick, right? Multifunction joystick, which allows the user to move this device in any direction, right? And this can be used by an individual with disabilities, locomotor disabilities, to navigate around different environments, right? And you've all seen perhaps examples of this. Okay. And then there's the Tesla full self-driving or FSD cars, right? So in full self-driving mode, autonomous vehicles will make all the decisions by themselves, right? So they're going to make decisions based, they will plan the path, they will avoid obstacles, they will choose the speed that it needs to operate in. When it goes from a small village road to a highway, it will change the speeds to appropriately match. It will make decisions on when it needs to change lanes in order to exit or enter the highway. So all sorts of driving decisions that are traditionally reserved for uh, a human user, an expert human user, can be and is offloaded to the system itself. And as you can tell from here, that autonomy is a spectrum, right? It's not a single fully autonomous or a non-autonomous system. So in a autonomous system, we had different grades of autonomy. While the full self-driving car can be thought of as a fully autonomous system, an adaptive cruise control can be thought of somewhere in between full autonomy and no autonomy at all, right? It will not make decisions of changing lanes. It will not be able to set its own speed limit, for example. It will not be able to make planning decisions, right? However, it does provide a little bit of autonomy, as the human can take proverbially a back seat and sort of relax a little bit. On the other hand, you have the wheelchair, which has full human intervention, right? So the human makes every decision as to where it must go, how it must be operated, how it can be, what speed it needs to be operated with, right? So when we look at these levels of autonomy, we have to understand that these levels of autonomy come from different capabilities. These capabilities start from the very basic of sensing what the environment looks like, right? This is an absolute basic necessity of any autonomous system. Without a sensing system, a autonomous system cannot exist. Without knowing what the external environment looks like, the autonomous system will not be able to operate. So basic requirement of an autonomous system would be a simple sensing paradigm, right? But beyond sensing, it's perception that matters. Perception combines sensing with the understanding of the sensory information, right? So sense and make predictions gives the ability to understand, right? And a vast majority, 1/3, 2/3 of all the devices that you would find out there, robots, would fall into this category of sense and understand, right? And then perhaps provide this information to a human user who can then respond accordingly, right? So when you start adding the response function to these environments, now you start getting semi-autonomous devices, right? So in the case of a self-driving cars, not only is it sensing and understanding what is the distance from the next car, it's also responding to it appropriately, right? Therefore, autonomy starts with response. Okay? And then the final stage would be the capability to learn, right? So as you know, in Tesla self-driving cars, the data that is gathered from these drive operations, these self-driving modes, is then sent back to the Tesla servers, where the models are actually updated over time and then fed back inside the card itself, so that the self-driving system can evolve over time. We can have reinforcement learning algorithms, like we saw in the previous lecture, where you can have gate adaptation based on the learning that it happens over the course of failures, right? So the final capability is that of evolution, or some form of self-improvement that is happening. And very, very small number of proportion of systems actually have this sort of self-autonomous capabilities. Okay. So when we talk about industrial robots, right? So now let's focus on industrial robots. We said that the definition of industrial robots as for the ISO standards that we had seen before talks about automatic, reprogrammable, multipurpose, but it does not talk about autonomous, right? It talks about automation, but not autonomous system. And there's a difference between autonomous and automation. So let's see what this difference might look like, right? So at the very basic level, right, of course, it's a complete human operation where the operator controls the machine fully at all times, right? In case of an earth mover, for example, this could be a simple earth mover that you would see in most construction sites where all the decisions are made by a operator. This is teleoperated in some sense, right? It's operated through a joystick. There is absolutely no sense, respond, evolve function built into it. Now, when we talk about automation, the overall control is with the machine, and the safety of the environment, the safety of the machine is with the human operator. But certain specific functions, like let's say, what angle should the bucket go into for optimizing the operation of the earth mover, could be left to a machine, right? So depending on the weight of the earth mover, perhaps it can adapt how much power goes to the bucket, right? So this sort of control can be thought of as an automation control, right? Where only certain specific parts of this operation, which does not have any bearing with the safe operation of this system, is given to uh, an automated system, right? Very function specific. Now, as we start moving from automation to semi-autonomous systems, we start giving more and more control to the robot in terms than the human, or the system than the human, right? So in a semi-autonomous system, the machine accomplishes at least a subset of the tasks without human operator. Perhaps the human mentions which object to pick up and which are the sequences of objects that need to be picked up. And the machine automatically determines the optimal path, avoiding the obstacles, and picks and places these objects in different configurations, right? While in a fully autonomous system, the human is completely out of the loop. The entire uh, environment is available to the robot for intervention, and all functions are given to the robot itself, including the decision of what sequences to plan, right? What to move, what not to move, how to move it, whether it is possible to move it or not. All of these operations are given to robots. So automation essentially has very, very limited control given to the machine, whereas in autonomy, you're essentially giving away far more control to the system than to the user, right? And the requirements for an automated and an autonomous system are very, very different, right? I mean, of course, it's an evolution above automation. Okay? And of course, in automation as well, as you can tell, there is a level of repeatability in automation, right? So you're executing the same tasks over and over again instead of the tasks being very abstract or unstructured, right? In autonomous system, there is a expectation that the system will be able to operate in an environment that is unstructured, that typically humans would be very, very good at doing. So autonomy adds that ability to have unstructured, have the ability to operate in an unstructured environment. Now, one example of automation that we are going to look at, and this is a counter example of automation and autonomy, and we've seen this system before, is the Da Vinci robot, right? And we had asked this question, can you look at this robot and say whether this is a fully autonomous robot? Is it human operated? The question is innately tied to the question of safety, right? And the question of skill. So when we saw videos of this robot, we saw that it requires a human to operate the robot at all times, while providing fidelity, while providing high levels of control that are probably not going to be achieved with a human operated cell. For example, when we saw this example of a grape being sutured, right, in a highly constricted space by a human operator externally, but using a robotic, surgical robotic tool like the Da Vinci robot. The question is, where do we place this on the spectrum of human operation? Is this an autonomous system? Is it a automatic system? Is this automation? Or is this fully human operated? Now, in order to understand this, we're going to use a framework, right? So we're going to start formalizing these frameworks to understand the details that need to go into the decision of assigning autonomy to a system. And as you will see, all of these are innately tied to the concept of safety, right? And the concept of effective execution of the commands, right? So this is from a paper, a very nice paper that was published in Nature. And I've linked the paper here, okay, which talks about definitions of autonomy in a surgical robotic system, right? So when answering whether a system is or should be a autonomous system in a surgical robotic scenario, we answer a series of questions. The first question that we start answering is, does the surgeon continuously control all motions of the system? Right? Is the surgeon responsible for controlling all the motions of the system? Now recall the videos of the Da Vinci robot. Would you answer yes or no to this question for the Da Vinci robot? Da Vinci is the surgical robot that we saw in the previous slide. Should we answer yes or no to this question? How many of you would like to answer yes? Yes, human controls all motion. A vast majority of us would agree the answer to that surgical robot like the Da Vinci robot, right? And when we answer yes to this question, we go to the left-hand side of this arm, right? So let's explore this left-hand side first before we come back to the right-hand side, okay? So in this left-hand side, after we have answered this question, whether the surgeon continuously controls all motion, and the answer is yes, then we ask another question. In addition to the surgeon controlling all this motion, does the system provide some sort of additional aid in execution of these surgical actions or monitoring of these surgical actions, right? So in the Da Vinci robot, we are going to ask, does the Da Vinci robot just simply execute the motions of the surgeon? Or does it provide some level of help in monitoring some form of a collision? Does it provide some form of safety? Does it make the tremors of the hand of a surgeon those functions? The answer is yes, it does, right? So it is not simply a system that takes the motion of a surgeon and transmits that as is to the surgical tool. It provides a little bit of assistance. Therefore, the Da Vinci robot falls into this level 1 autonomy when it comes to surgical robots. As you can see, it's a very, very low level of autonomy because the system provides only passive support, tremor filtration, maybe some form of active guidance, haptic feedback, feedback when you collide with an object, feedback when you're cutting into a soft tissue versus a much more denser tissue. So that sort of feedback is present. So there is some form of aiding in the surgical in this robot, but the execution of the task is left to the human user or the expert surgeon. So this is a level 1 autonomous robot. So you can see in terms of surgical robotics, the state-of-the-art systems that have made it out into the commercial market are still at level 1 autonomy, right? So what are these higher levels of autonomy? So if we start looking at the higher levels of autonomy, we have to go back to this first question and answer, does the surgeon continuously control all motions? And part of that answer has to be no. Not all of the motions. If I want to move up my level of autonomy, I need to give some motion control to the robot. Okay. Now, when we have given this control to the robot, then we ask certain additional questions, right? The next question that we ask is, does the system generate and update the strategies for the task? Let's say there's a there's a gallbladder surgery that is going on. Is the system capable of independently generating a plan or a strategy for updating the motion of this robot? If no, right, we say that it is a level 2 autonomy where the surgeon provides the parameters. The surgeon will essentially show the robot, maybe in simulation, what sort of path it needs to execute, what sort of cutting forces it needs to needs to execute, and then the system takes over. So the surgeon can take a back seat. Right? It's simply a recording of the surgeon's actions that is getting transmitted and executed in later on. Right? However, if we allow the system to make those decisions in real time, then we have to ask another question. Does the system, right, independently select the optimal strategy? Right? So in the previous case, we saw that, yes, the system generates the strategy. So let's say if I have a patient who's supposed to undergo a knee surgery or a gallbladder surgery, the system can generate different strategies. So the first question asks whether we allow the system to generate the strategies or not. If we say yes to that question, then we ask, does the system also get to choose which is the right strategy? Not just generation of the strategies, but also whether path A is correct, path A and X cutting force is better than path B and Y cutting force. If we do not give it that level of autonomy, we call this a conditional autonomy, where the system independently generates these tasks and these strategies, but the surgeon takes the decision as to which one is the best of these three, right? And the system then takes over and executes it. This is one level of autonomy higher than level 2. Now, if we give the robot the ability to not just plan, but also choose, right? So it's now making the decision of which independent strategy to choose. Then we ask the last question, right? Is a human necessary to approve this plan or not? So this is like a safety check. The system has generated 10 different plans. It has then chosen which plan is the best plan. And then, do we at all need a surgeon to vet this plan or to say that, okay, I sign off on this plan and this approval is required? If a surgeon's approval is required, we still need a little bit of human intervention. This is a very high level of autonomy where the system has sensed and planned and chosen the right optimal plan. But the question of whether to act or not is still left to a human intervention, right? And perhaps this is required since there is a lot of variation between different patients. There's a lot of variation between the same patient and different kinds of surgery. So this is the highest level of autonomy that would be required, that would require human intervention. And then in full autonomy, the system takes all of these decisions themselves, including the decision of whether the plan is appropriate or not. And we are nowhere close to this level of autonomy, right? So this provides you with a nice framework of how to answer questions about autonomy, particularly in the case of surgical robotics. This is one paradigm, one framework where we can systematically identify what levels of autonomy are to be taken. And we can take some hints and we can take some inspiration from this framework and, and identify the right questions to ask about autonomy. It is not just about whether a task can be fully given to the user. It is also about the safety and the effectiveness of that plan, right? So when we ask these questions about level 2, level 3, and level 4 autonomy, what we were indirectly asking was that out of the strategies that were chosen by the surgical robot, which one does the job more effectively and safely, right? Through these questions, we were talking about effectiveness and safety. And there is a fair amount of human judgment involved in this. And once we start delegating the effectiveness and the safety aspects of these safety critical tasks towards robots, that's when we start building more and more higher levels of autonomy. Okay. So we have already answered this. Is the Da Vinci robot an autonomous system? Yes, it is. It is a level 1 autonomy. So it's a spectrum. We cannot say that the Da Vinci robot is non-autonomous or it has no autonomy at all. It has a certain level of autonomy, which is low on the spectrum of possible levels of autonomy that can be achieved later. Okay? So when we talk about autonomy, as we said, are we asking the right questions, right? So when we look at these robots, we saw these videos of robots doing cleaning and so on, right? So it's able to automatically plan the path. It's automatically able to execute this plan. And it's automatically able to return back to base. It's able to protect itself from harm, right? We saw these examples of where robot will automatically avoid the stairs. It will avoid falling down from the stairs and hurting itself. But when we talk about autonomy, we also have to talk about effectiveness, right? Now, if I look at this robot, it is called a robotic cleaner, but is it really offering me the ability to clean? So it is only performing a certain task, a certain very specific task. And within that task, there are lots of limitations in what it can achieve. Like if you look at this photo, if we ask this robot to clean the space, it is probably going to move all of these objects or avoid all of these objects and clean in between. But is that really a form of cleaning? When we talk about autonomy of robots, we would probably regard these robotic cleaners as fully autonomous systems. They do not require any human intervention. They do the mapping, they do everything. But we don't talk about the effectiveness of the robot, even though there is a level of autonomy involved. So asking the right questions when you're talking about autonomy is very, very important. So can we build a framework to understand the level of autonomy that is appropriate and talk about the effectiveness of this paradigm in the Sense Plan Act model, right? So we have looked at sensing, planning, and acting. And in all of these stages, we need to understand what is the level of autonomy that is attributed to the robot. And we're going to take two examples of it. The first is that of a teleoperated system. An example of a teleoperated navigation system would be a drone, right? So in a drone, as you know, it is almost fully human operated. You can offload certain operations to the drone itself. For example, you can ask it to circle a certain area. It will also avoid obstacles on your behalf. So if there's a tree or if there's some obstacle in between, it is going to ensure that it doesn't hit that obstacle. So it has the ability to protect itself from that harm. And then we have semi-autonomous navigation systems. Okay? So semi-autonomous navigation system would be an adaptive cruise control system. Okay. So in an adaptive cruise control system, you are still in control of the direction in which the car is moving, just like a teleoperation system. But it's making certain decisions about the speed, it's making certain decisions about the distance that it needs to act. It's also making certain decisions about whether to brake or not, whether to accelerate or not, right? And we're going to talk about these two systems simultaneously and look at them from the sense, plan, act paradigm. So in this, we divide the autonomy into three parts: autonomy in sensing, autonomy in planning, and autonomy in acting. Okay. So the top line shows the case for the semi-autonomous navigation, so an adaptive cruise control system. And the dotted line here shows the level of autonomy for the assisted teleoperated navigation, or think of it as a drone. So in the sensing paradigm, right, essentially, you can see that most of the sensing in a semi-autonomous navigation system, or an autonomous navigation system for that matter, is almost fully attributed to a robot, right? It is fully given to a robot. Whereas in assisted teleoperated navigation, there is a level of sensing available. There are some LiDARs and so on. But the direction in which you flow, what velocity you are going at, is still left to the user, right? So the level of autonomy or the level of allocation of resources to the human is still relatively low in cases of semi-autonomous navigation. The amount of duties allocated to the human, right? Now, in the plan zone, right? So if I move to planning, I see that in case of semi-autonomous navigation, the planning of what velocity to choose, how much distance to maintain, is given to the robot, right? Whereas in a teleoperated navigation system, no such control is given to the robot. So the amount of autonomy in the planning stage is again much lower compared to that of a semi-autonomous navigation system. It's mostly allocated to the human, right? And as a result, you see a lot of drones being lost because of poor ability to control it. And finally, in acting, right? When it comes to actuation, this is in a semi-autonomous system, partially given to the robot and partially given to the human, right? So, of course, the distance is maintained by the robot, the velocity is controlled by the robot, the acceleration is controlled by the robot, the navigation is still up to the user, right? So it's still high, but limited. Whereas in a drone system or an assisted teleoperation navigation system, again, if you look at the actuation, right, the velocity is not controlled, the motors are not being directly controlled by the user, right? The action of moving about, maintaining the trajectory, all of these are given to the user. To follow a particular trajectory, user must decide what velocity, what direction, what orientation to fly in, right? So overall, you can see that an assisted navigation system has lower levels of autonomy across the spectrum of sensing, planning, and acting, right? And we can apply this to more complex systems. So let's take an example. So we are adopting a framework to try and understand the levels of autonomy in a particular system, any system for that matter. So I'm going to take about 5 to 10 more minutes and then we'll be okay. So once again, this is from a paper, right, of Journal of Human Robot Interaction. So please go through this paper if you're interested. It's a fairly easy and accessible paper. So we're going to take one example, okay? And we're going to try and see how we can attribute levels of autonomy to a robot based on the task criticality, the complexity of the environment, and the accountability or the sense of trust that one can attribute to a robot. So let's say we talk about a service robot, a robot that is meant or designed to assist with medication management for older adults, right? So for older people in a house or in a hospital setting, it will automatically bring the, well, we can decide what it does automatically, but it will essentially assist the user in management of medication, right? So when we talk about this sort of a system, the first question is asked that we ask is, what task is the robot to perform? And in understanding what task it has to perform, we ask about three different aspects of it. The criticality of the task. How critical is this task? If this task fails, right? What is the consequence of a failure in this task? I would say that in a service robot that assists with medication, task criticality is extremely high. If the medicine is not chosen correctly or not brought at the right time or is given to the incorrect person, all of these variables have a very, very high cost involved with it, right? So simultaneously, depending on the environment that we talk about, we can talk about the environmental complexity. So let's say if it's in a home, perhaps if it's a service robot meant to be in a home, the environmental complexity of a home is far less than that of a hospital. So if it's a service robot that is operating in a hospital that goes to the pharmacy, automatically picks up the intended medicines, brings it back to the room and gives it to the appropriate patient, the task complexity is far higher than a home-based setting, where one would only require fetching of the medicines from a certain cabinet or from a certain box and feed it to a designated user, right? The number of users that are present inside a home use environment is also going to be low. So in a home-based setting, this environmental complexity is low. Whereas if you want to build a system for a hospital, this environmental complexity would be very, very high. It would be a highly complex, unstructured environment, right? And then the question of accountability comes, right? So let's say something fails. We spoke about the criticality of the task. So of course, the task is extremely critical. But if it fails, right, even with a high task criticality, if it fails, who is responsible? Question of responsibility also is something that has to be maintained. So for example, in a surgical robot, for example, who would take responsibility for a surgical error, right? In case of a surgical robot. And these are very broad ethical questions that we must answer. Okay. So once we've answered that the task criticality is high, the environmental complexity is medium, and the accountability has to be high, because if it's a service robot made for medication, one must be extremely accountable, and there needs to be a human that needs to be accountable for it, right? So then we start breaking up what aspects of the task should, not can, should. You can automate a lot of things, but should the robot perform based on the task criticality, environmental complexity, and accountability? And we break it down into the sense, plan, act paradigm. So in terms of sensing, if a service robot has to give proper medication, it has to understand which medication it's picking up, which might be extremely difficult to identify, right? As you know, most medications, at least in India, look almost the same. They come in silver foil packets. Maybe if we transfer these into a medicine cabinet with clearly marked barcodes or so on and so forth, it might be easy for a robot to identify. However, in a naturalistic setting, in a more generalized case, where we would not want any human intervention, picking up individual medication, which is the primary function of this, which require very, very complex sensing mechanisms. Individual medication may be difficult to identify. In terms of planning, once it's able to identify the medication, it might be fairly easy for it to pick up that medication and plan the path to bringing it back to the user. In a hospital setting, this could be a fixed path within the hospital to a particular room or a particular bed. In a home setting, which is a medium complexity setting, it might be simply navigating through the rooms, identifying the user, and then giving it to the correct user. Right? And again, delivering, right? The planning is one thing. So planning how to navigate through the environment is one thing. Acting on it may also be quite easy, particularly if it's a wheeled robot. Right? So on the plan and act front, we see that we can ascribe higher levels of autonomy because these are easy tasks. These are tasks that have lower accountability, perhaps in some sense. However, the sensing of both the environment, including the medicine, and the right of person to deliver it to has to be very, very high. So that has to have a very high level of accountability and a high level of trust criticality. Right? And it's a difficult function to achieve. Right? So based on these, now we take a qualitative decision. On the spectrum of autonomy, starting from fully manual to a fully autonomous system, we see that there are many, many stages, right? Teleoperation, batch processing, decision support, shared control with human initiative, shared control with robot initiative, supervisory control, full autonomy. Just as we saw in the spectrum of autonomy for surgical robots, you also see the spectrum appearing for simple service robots or general robots. So now, based on the Sense Plan Act, we now need to think what level of autonomy can the robot or should the robot be categorized into? Okay? So this is my personal opinion. There's no right or wrong answer, right? So depending on the task criticality, I feel, given the current state of the art in planning, acting, and sensing, that the ideal approach that makes the system highly robust to the task criticality and accountability ascribed to the system. Perhaps the user should pick the medicine, finalize the medicine, put it inside certain boxes, and the robot is only responsible for the delivery of that medicine. Okay? So perhaps the level of autonomy that is appropriate for this, is somewhere in between decision support and teleoperation, right? If the user doing most of the tasks in terms of sensing and planning, the robot is only involved in acting out these variables, right? Additionally, once we make these choices, right, once we have ascribed these levels of autonomy, we also need to think about certain socio-economic and human-related factors, right? Social variables and human-related factors. The first of which could be about acceptance, effectiveness. Our older adults will be the main users of these autonomous systems, will be ready to trust these systems and accept these systems. Can the medicine delivery be trusted? Right? And finally, does it actually help the user? Does the ascribing of autonomy help the user in either reducing the level of medication errors in medication, or it involves reducing the burden of having to fetch? Let's say there's some older adult who's not able to move, is completely immobile. Does it actually help them? Right? So now with all of these parameters, you may need to change the level of autonomy that you ascribe to this system, depending on what your answers to these questions could be. At the current scenario, perhaps older adults will not be very, very comfortable with a robotic technology that doesn't make this decision for them, right? So this, as you can see, is a fairly subjective method of looking at this problem of ascribing autonomy. But this gives a fair framework to start asking the right questions. Okay? So this is an example that we solve. And now I would like you to think about and come up with the right level of autonomy. Again, there is no right or wrong answer. But think of a robot that does search and rescue for firefighters, right? The robot is responsible for entering buildings during fire, and it is responsible for finding and rescuing individuals who are trapped in that building. So your question here, the questions that you will need to ask is, how critical is this task? What is the environmental complexity of such a robot? And what is the accountability? And then you need to ask how much of these operations can be automated in the sensing domain, planning domain, and acting domain. Okay? And then ascribe a level of autonomy to it. And then ask whether firefighters are ready to accept, whether the public is ready to accept. Can we recognize hazards appropriately? Will it make firefighting actually easier and safer for firefighters, right? The end users. Once you do this, start thinking about the appropriate level of autonomy that is appropriate for this scenario. Okay, so with that, I'm going to stop here today. We're going to talk about the ethical concerns of autonomy in the next lecture, okay, in the next class. And then we're going to move towards understanding the jargon. So we're going to look at data sheets of different robots and start deciphering jargons that are present inside the robot, so that when you go to an industrial role, when you go to the market to buy parts for a robotic system, you know exactly what you're buying. So that's for the next lecture. So with that, I'll conclude my lecture here. The next session, which will be taken by Professor Arnab, will start at 12:40. Okay. If you have any questions, I'll be here to answer them. Yes, Jari, please go ahead.
A totally a different chapter. Actually, I have just forwarded my mail that I have sent to you on 31st of March. So
Okay.
can you please check it, the executive, the program, I mean, the email
Okay.
address?
Yes.
Can you
I'm
please
aware of
check
your,
it?
yes, I'm aware of your mail. We will respond to it.
Okay, thank you.
Yes.
Thank
And I
you.
think your question was about execution of the project and so on, right?
Yeah, one shot.
Yes. Yes.
Okay.
We will
Thank
respond
you.
to it. Thank you so
Thank you,
much for
Vishnu.
reminding.
Thank you very
Yes. Thank you. Yes, I see two hands. Please go ahead. I'm not able to see who is raising the hands. Sorry.
Agnishekhar here.
Yeah, Agnishekhar,
Uh,
please go ahead.
yes, one question from the previous lecture that
Yeah.
you had said that like the pneumatic robots or the pneumatically operated robots,
Uh-huh.
they are not having very high payload capacity.
Mhm.
If I am right in understanding this, then what is the weight we are looking at which makes it as a high payload capacity?
Yeah, so please hold off this question for another class. We talk
Okay.
about payloads in the next class. So we'll talk
Okay.
about the concept of payloads. We'll talk about how do you decide the appropriate payload for a particular robot. So that comes next class. And of course, then we have a separate module on actuators altogether. So I think all of your questions will get answered then. So I'm just requesting you to just wait till then. Okay.
Thank you.
If not, please come back. Okay. If you're still not satisfied, please come back. Okay?
Sure. Thank you.
Thanks. All right. Any other questions? So I see a number of. Okay. So Abhinav mentioned it's possible for project, and I'm planning to go to Masters for Robotics. Like, please visit you at IIT Delhi campus to discuss the same. Yes. I mean, what I would suggest is, see, all of you are welcome to visit the IIT Delhi campus. However, it may not be possible for us to meet you on any particular day because we are all very, very busy with other commitments as well. As you can see, just like you, we are working on weekends as well. So please give us a heads up if you're coming and what is it that you would like to meet us regarding. So you can send us a mail in advance, at least I would say 2 weeks in advance if possible, to give us some time to plan your visit. However, please also realize that you have a campus immersion at the end of the course, right? When you finish, you're going to invite every one of you to IIT Delhi. That's a more formal way of actually visiting the campus, and where we'll spend an entire day with you, talking about your experience, and we're going to help you meet some industry folks who are going to talk about their journeys and so on. So we have an entire day or two planned with you. So that's one opportunity. But if you're in the city and you want to drop by, please do. Please just write to us. Okay. Yeah. So Abhinav, like I said, please reach out over mail and we can see what we can do. So right now I'm not in campus, for example. I'm in Kolkata. There's a family emergency which I'm attending to. So at different points of time, either myself or Arnab or both of us may not be present. So please reach out to us over email, and we'll try to see if we can arrange a one-on-one interaction. Yeah. All right. Um, I don't see any other hands raised or any other questions that are pending. In that case, we will reconvene at 12:40, please. Okay. Thank you so much, and I will speak to you in the next lecture. Thanks a lot. Take care.
Thanks, Vishnu. Thank you very much.
Thank you. Thank you very much.
Thank you, sir. Bye, sir.
All right, so I think we are at 12:41. So I think the previous session ended a while back. So you've all had a chance to take a break. And I'm also hoping that all of you are enjoying the sessions thoroughly. And it's been very, very insightful, right? So, all righty. So just one mistake in this is batch 2, not batch 1. Fix that mistake. All right. All right, so let's get started. So we are going to talk about the kinematics and kinetics of robots, which is more of a technical topic. I'm just hoping that I'm audible, right? Like, can somebody just respond that you're able to hear me?
Yes.
Okay, perfect. Thank you. Yeah, just making sure that. Thank you. All right. So we are going to talk about kinematics and kinetics of robots, which are very important quantities. Typically, if you look from a very technical and mathematical standpoint, how do you design a robot with the right set of motions and with the right set of actuations and steps? So this is where the fundamentals of kinematics and kinetics become really, really important. So I'm going to touch base upon some of this, not dive too much into the math, because this might be not super beneficial for many of you, and your robots might vary quite a bit from that. but we are going to still nevertheless touch upon some of the math, understand some of the concepts of kinematics and kinetics, which are all useful for the designing of the robots, right? So let's get started with this interesting topic. Yeah. All right, so first question is, what is kinematics? So kinematics is what we visually observe of a body in motion is known as the kinematics of movement. So kinematics has everything to do with motion, right? It's the study of size, sequencing, and timing of movement without regard for the forces that cause or result from the motion, right? So it has everything to do with motion without thinking of what forces may have caused that motion or would have resulted from that motion, right? The kinematics of an exercise, for example, or a sports skill is commonly known as a form or a technique. So this picture kind of encompasses some kinematics, which is basically the focus is the motion, irrespective of so many forces which might be apparent. Like there could be a gravitational force, like if you're going up the hill, there is force of friction. There are so many other forces which are acting on the bicycle and the rider who is trying to propel the bicycle. But that's not important when you're talking about kinematics. Kinematics, only the motion in terms of speed, how quickly things are moving, that is important. So hopefully this first statement is clear. What is kinematics? Next is, what is kinetics? Or sometime you may pronounce it as kinetics, right? It is the study of forces, including internal forces such as muscle forces and external forces, the forces of gravity and the forces exchanged by the bat and ball, right? You would see something very similar in cricket, even though this one is not cricket, right? So kinetics has everything to do with the study of forces. Unlike kinematics, which is just study of motion, kinetics has everything to do with the study of forces, right? So this is the second concept. If you're looking at rigid body mechanics, which is one of the main driving factor for all your robotic space motion. So robots are quite complex, as you know, like there are a lot of joints, there are a lot of actuation systems, which are overall trying to create a motion, which is a desirable type of motion for the robot. And of course, the robot has certain things to solve and go to a certain place. And there are so many other milestones which the robot has to achieve. But what forms as the fundamental backbone of any of the robot systems is the rigid body mechanics. So rigid body mechanics can be broadly classified into statics and dynamics. Under statics comes things which are completely at the state of rest or are moving at a constant velocity, right? So typically, if you have, let's say, a car moving at constant velocity, or a robot is just moving at a constant velocity, or is motionless. So that is where the equations of statics will work, or the fundamentals of statics will work. Right? Under constant velocity, you have kinematics and kinetics, which can happen. Then the other classification is dynamics, which most of the systems are in. Dynamics is where everything is in the state of a dynamic motion, right? And while this is happening, there are so many forces which are getting exerted and which are getting exerted from the body or from the robot to the other systems around it, right? So under dynamics also, you have kinematics and kinetics. So what do we know? Broad areas of under the rigid body mechanics are statics and dynamics. Under statics, you have a motionless or a static condition completely, and then you have a constant velocity condition, under which kinematics and kinetics can both be observed. Even under dynamics, which is the other classification, you will observe kinematics and kinetics, right? So these are typically the options which you have for any robots, any human motion and things like that, right? Further, what is kinematics? There are a lot to do with spatial and temporal characteristics, right? So this is typically qualitative or quantitative in form. There could be linear motion or angular motion, right? So spatial is, let's say in this particular room, I consider the one corner of the room as the origin, right? Which is 0, 0, 0 in the Cartesian coordinate system. So where exactly a particular finger of my robot is, or particular joint of my robot is with respect to that 0, 0, 0, right? That is the spatial understanding. Temporal is basically time-based understanding. the things which you mentioned can be quantitative, they can be qualitative. Typically, we engineers talk in terms of quantities. We talk in terms of this robot is going to go for 1 meter, turn by, let's say, 25 centimeters, put its arms up, tweak the finger, have an angle rotation of theta, which is 30 degrees, things like that. Qualitative is this robot is supposed to go to that car or go to that particular person and give this coffee cup, right? That is more of a qualitative, where it has to have a lot of feedback and things like that. And the typical motions which you see in kinematics are either linear or angular. So something can rotate or move in spirals or things like that, or it could move forward, sideways, or up and above, right? So linear or angular motion, basic kinematic concepts includes the variables for describing the motion, right? Reference systems for describing motions of the human body and its segments or robotic body and its segments. Guidelines for describing the motions. So there are several laws which govern how systems move or how bodies move. Many of these you may have studied in physics lecture, right? Back in the 10th or 12th grade, like, these are typical common things. So reference system is very important. With reference to what are we referring? Like I've just given you an example of an origin. It could be that the origin is somewhere else. And let's say the robot as a whole you're looking at with the Cartesian convention system, which is a global Cartesian system. It could be that you have a lot of local coordinate systems, how the fingers are moving with respect to the tip of the toe of that robot, right? Let's say it's a humanoid robot. So these things are very, very important to have a reference systems, have a clear set of guidelines, and then clear description of variables for describing the motion. What are we talking about? Is it variable? Is it a speed along the x-axis, y-axis, z-axis, or is it acceleration? What is exactly going on? That needs to be very clearly defined. Okay. So kinematic variables are typically time-based, position-based, displacement and distance. Many of you may be knowing what is the difference between distance and displacement. Displacement is the shortest path between 2 points, and distance is the entire path traversed, whether you're going in circles or going to n number of places and finally coming to the final point. That entire distance covered is the distance, right? And just the shortest distance between those points is the displacement. Velocity is displacement divided by time. The entire displacement of the shortest path divided by the total time taken to reach that shortest path. Distance is the entire distance, whether you're going in spirals, circles, or you have gone to 10 different locations before you reach to another point. That entire distance divided by the total time taken. That is speed, right? And then you have acceleration. So we typically know whenever there is an acceleration, there is a force which is acting on a system which is causing that acceleration to happen. That's why force is given by force m into a, mass times acceleration, right? So typically these are some of the variables you will be studying or talking about when you're talking about kinematic variables: time, position, displacement, distance, velocity, speed, and acceleration, right? Let's look further. First is time or temporal analysis. So the questions to answer is when, how often, in what order, how long. So what you see below is a human gait cycle. Gait cycle is nothing but it's the way we walk normally, right? So typically from 1 foot touching the ground with a heel strike, which you see in the first person, all the way till the load shifting, load acceptance, load shifting, while the other foot swings and comes to the front, and you complete the gait cycle. So we are going to talk about gait cycle at length, because this is where, when, how often the forces are to be applied, how often the speeds change, in what order, how long, these questions become very, very relevant. Most of the robots which you're trying to build, which are not wheeled robots per se, which are more towards trying to simulate the human gait, like the humanoids, for example, or similar looking robots, which the world is trying to eye for. We are focused on the replicating the human gait. That's why we want to understand the human gait very, very clearly. So the most basic analysis examples are, you talk about cadence, strike time, temporal patterning. You do not have to worry about these terms. I'll explain them one by one, right, as we go through. Temporal patterning is more of like the time based events which happens in the different kinds of muscles which is shown during the stance and the swing phase. So these are the typical two phases of your walking. So whenever your foot is not on the ground, one of your foot is always not on the ground during walking, unless there are these slight overlaps where both the feet are on the ground. One is about to take the heel strike, the other is going through a toe off. Unless that is happening, everything is known as stance. Whenever it is on the ground, it is known as stance. Whenever it is off the ground, not on the ground, it is known as the swing phase. So from a time standpoint, what are the different muscles doing in the body during these phases? This is what is shown in this plot. When are they getting activated? When are they not activated? So how is this information relevant to robotics? Right, that question comes to our mind. This is relevant because this is exactly where you may not have muscles, but you will have actuation systems in place in terms of motors, linear rails and things like that, which is supposed to be providing that gait simulation or gait functioning to your robot or your humanoid robot, right? That is where you need to make sure that this temporal patterning or the time-based patterning, when each or one of these sections are getting activated or the motors starting and firing, that should be rightly timed. Otherwise, the robot will lose its balance. If both the feet are on swing phase, of course, it's going to fall down. If both are on the ground, you're not going to be able to move forward. Right? So the human gait cycle is very, very unique and very important to understand to make sure that you can create a robot which can walk like the humans, even though it may not have the entire body like the humans, right? So that's why this knowledge is very important. What is the time patterning of the different muscle firing? Similarly, you devise your actuation systems. Next is position, where the key question is where. Where can be applied to a lot of things. So let's say, let's assume I'm a humanoid robot and I'm holding onto this cup. So where could be a lot of things? Where is my elbow? That could be one of the question. Where is the tip of the cup? That is another question. So it depends where you are applying the term where, right? And it has to be mentioned or positioned in terms of coordinate systems. So position is nothing but the location in space relative to some reference point, like linear position in X, Y, and Z coordinates. It could have angular positions and specific units which are around it. Right? So how can something have angular positions? Like, let's say this is my arm and all I need to do is probably not rotate my, probably not move my arm, like translate my arm, but just rotate it slightly. Like, let's say a robot has been able to pick the cup and bring it up to here, but still I'm not able to sip the tea. So all that needs to do is rotate a little bit so that it comes closer to my mouth, right? And I'm able to sip the tea. And it has to rotate a little bit like this also, so that I'm able to actually take the tea. Otherwise the tea is like this, right? So these are the angular positions which comes into account, right? So where is the important question of the position? Okay, when you're talking about distance and displacement, the question is very clearly how far. I've already told you what the displacement and distance is. Displacement is a vector quantity. Distance is a scalar quantity. So just a quick refresher. I think everybody has studied in physics. Scalar is something which has which has basically a magnitude but no direction. Vector quantity is something which is directional, which has a magnitude and a direction. So typically, if somebody travels from A to B, B to C, then the displacement vector is AC, right? Which can be easily derived by the Pythagoras theorem. The magnitude can be derived and you can have a vector addition. So just a quick refresher into some of the physics which we have already studied in our high school. Typically. What is velocity and acceleration? Typically, it's a vector quantity. Velocity is a vector quantity because it's a ratio of displacement and time. And acceleration is more of a vector quantity, which is a ratio of basically the velocity and the time, right? Given by A, right? So the units can be meters per second for velocity and angles, which is in degrees per second for any kind of rotational, which is given by the omega. Omega is the symbol for, or the W, small w is the symbol for velocity, angular velocity, and alpha is the symbol for acceleration or the angular acceleration in this particular case, right? Which is given by degree per second squared. So this typically provides insights, acceleration term of the be it angular or linear acceleration gives us insights into the forces or the torques, right? So these are very, very important. Okay, so now that we have refreshed some of the key measurement pointers, which we will be talking about in many of our studies and things which we go on through the lectures today, let's talk about the basic kinematic concepts. So it all depends on the types of motions, the variables describing the motion, reference systems for describing the motion of the human body and its segments, which we have seen, and guidelines for describing the motion. So let's look at the reference systems. So what can you have? You could have an origin. So you must define an origin reference system to quantify the kinematics. You could have a positive x, positive negative y, and similar for the z. So this is typically a linear reference system. Then you could have an angular reference system where you could either put your angles in degrees or radians. So pi is the entire circle. So pi by 2 is more of half the circle and so forth, right? Sorry, my bad. 2 pi is a full revolution. So 2 pi is the entire one. Pi is like the half the circle, and like half pi is like half the radians, like this is 180 degrees. And then so forth. Like you can have the different variations of 1/4 of a pi or 1/4 of a revolution. So the entire revolution, as you all know, is 360 degrees, right? So you can measure a motor's rotation. Most of the motors which we would place in for the robots or any kind of motions are going to typically rotate. Whether you want to change this rotational system to a possible linear system is up to you. How can you do that? So using a pulley mechanism, pulley and some kind of a belt mechanism or a chain sprocket assembly. What does the chain sprocket assembly do? You're converting rotation into linear motion, right? So many of the linear things, or you can convert linear motions into further linear motions, which are geared with assembly of gears and things like that. So these are typically present in the joints for majority of the robots. So this is the angular reference system, right? Okay, next is if you look at the relative reference system, this is very important. Now, where are the angles in reference to? So just look at these two diagrams. The first one is showing you an angle which is between the, basically your bicep area and like the front arm area. So this is in the upper extremity. You're looking at the angle between at the elbow region, like between these two. If you look at the other picture, you're basically designating an angle with reference to the bottom line, which is your surface or the ground, right? So how should you typically consider it? So the answer to that is you could consider either of that, both are okay, but you have to define very explicitly that what is your reference system. So what you're seeing on the left side is based out of a lot of local coordinate system, and what you see on the right side is based out of the global coordinate systems. Global coordinate system is when, let's assume you have put the surface or the ground as a positive x-axis, right? The direction at which this person is moving. That could be a negative x-axis or a positive x-axis. The other side is negative x-axis. You're taking all the angular measurements with respect to the surface. And in the other picture, the first picture, you're taking all the angular measurements with respect to the different linkages which are forming the joints. So it depends. What you take, just stick with the same reference system while you make your calculations, right? So having said that, we do not build robots by just waking up and just designing something and say like, let us build this into a robot and let's see how it functions and then we will improvise. It never happens like that. There is a lot of mathematical calculation and background work which is involved in the designing of the robots, designing of all the linkages, how much of a rotation, let's say 20-degree of rotation is going to create what kind of a motion, and it's going to take, let's say my cup, where if this was like more of a robotic arm, that needs to be properly benchmarked. If we do not know the final calculations, that after 20 rotations of, like, let's say my fingers, 20-degree rotations of my fingers, maybe 30-degree rotation of the wrist, if it happens so that the teacup is still here, then the robot has not succeeded in its job. That's why there needs to be thorough calculation on what all rotations, what all translations needs to happen so that you are able to reach to your final destination, which is in this particular case to my face, right? Like, so that I'm able to take my tea. Okay. So relative reference systems, like I said, there are a lot of interesting concepts which you can put. This is dependent on fundamental standing positions and anatomical standing positions. So what do you consider as the initial reference is very, very important, right? So one example of taking or considering an initial condition of the reference system is that all joints are 0-degree except the ankle, which is at 90-degree, and the forearm varies. This is one way of looking at the concept. But in typical human form, if you're trying to convert all the joint motions or all the motions of the human body into a humanoid, you have to consider for all the joints realistic values of the angles, right? That is typically what is done. So then there is a reference system for measuring joint positions or the displacements. So how do you measure that? So left side shows you one way of measuring, where you're basically considering this arm, which is, so look at any of your upper extremity, which is the upper arm, the one which is your biceps, like this arm is considered to be the line from which the angle is taken of the lower arm, right? Based on that, you know what is the joint angle, and you're taking it from the other direction, not the smaller angle. So it's at a 140-degree. This is one way of taking the measurement. The other way of taking the measurement is what you see on the right side. You're taking a measurement of the foot angle, which is more of a, this is known as plantar flexion, by the way. So when you, so the bottom part of your foot, or the basically the sole of your foot, that is known as a plantar component, right, of your foot. So if you are going downward in your foot direction, it is known as plantar flexion. If you're going towards the top, like you're raising your foot, like that is known as dorsiflexion. So you're typically looking at this angle measurement from the, considering if you put 2 points, one on your thumb or the big toe and one on your heel, draw a straight line that will give you the average line of your foot. If you take any angle, how much your foot is moving from that reference point, that angle is moving. That's how you know the angle of dorsiflexion or plantar flexion. Dorsi is up, plantar is down, right? So these are the different reference systems for measuring the joint position and displacement. Extremely important, because unless you know how many rotations of the motor is leading to what kind of a positioning for every component of a robot, you will not be able to determine that what the robot as a whole is going to achieve. Hopefully this part is clear. So if I'm supposed to go from my home to the next house in my locality, it is not like I'm only putting all the forces and motions on one foot. There is a lot of coordination which is happening between the joints. There are so many joints which are involved, which is causing my entire gait to happen. There is a hand movement, there is a hip movement, spinal movement. So in order to understand all these specific coordinations, you need to be measuring all these joint motions, and they're typically in terms of like angles and with respect to a reference system which is in place. So these are two ways of referencing which I wanted to mention, right? Further, if you look at some other angles, you can well see one is known as a pronation, one is supination, right? You're rotating something like this. This is a clear rotation. Let's say if you, in a humanoid, you're trying to rotate the wrist like this. So there needs to be a motor which does this rotation. How do you measure those final outcomes? Based on the number of rotations, right? You can very well see that the whole rotation is not possible. This might be 180 degree. This may be less than 180 degrees. This could be 160 degrees. So these important parameters are important to be notified. Okay, now let's talk about qualitative versus quantitative. What is a qualitative measurement? Qualitative measurement pertains to the quality without the use of numbers. So this is typically what a sports person or an athlete or a doctor, they will typically talk in terms of qualitative parameters. For example, this person is strong, this person is skillful, this person is agile, flexible, fast. How fast, how strong, that is not known. These are just ways to say that something is a nice quality. But engineers always talk in terms of numbers, right? So if you are saying that somebody is running fast, how fast? That should be mentioned. Running speed is 5 meters per second or 7 meters per second. If somebody is tall, what is the height? So this specific height has to be mentioned in terms of numbers. If somebody has put on some weight and is looking bulky, what is the weight? So all these numbers have to be quickly put in place. So that is the difference between a qualitative versus quantitative measurement. Hopefully this part is clear to you. Okay, how this is important for the robot? Quantitatively, same example. Let's say I'm reading my newspaper. The robot is supposed to bring the teapot and basically give it on my coffee cup, or the coffee pot and bring it to my coffee cup, pour some coffee while I'm reading newspaper. So what did the robot do? Due to miscalculations, quantitatively, the robot missed the coffee cup by 15 centimeters. This is how you quantitatively say things, and that is what makes sense to a robotics field, right? Qualitatively, what do you say? What the other people who don't have knowledge about robotics, they will say the robot just malfunctioned. How has it malfunctioned? By what entity? What is the margin of error? These things are not known, right? So that's why it is very important to describe kinetics and kinematics in terms of quantities. Otherwise, we'll not be able to design an effective robot which is able to provide an effective solution, right? Let's talk about now kinematics in robotic systems. What happens? This is what happens. So basic problem of robotic kinematics is this. There are some motor coordinates, motor movements, joint movements. There are some transformations and end effector. So what does this mean? So let's say I'm supposed to bring this cup here. And my hand is here. What are the kind of joint motions which are needed? My hand needs to twist like this. This needs to come like this. Of course, pick the cup. While it is doing that, it is supposed to be holding a certain amount of load. So it should not be like the cup just bends like this. So it should be able to support a certain amount of load in normal cases. Then it would need to twist like this and maybe come a little further and tilt like this before I am able to sip my tea. So that includes a lot of joint rotations, lot of joint movements, a lot of linear movements which are in coordination. If you do them one after another, then the robot will take forever to bring the tea to you. So it will never happen like this, now this, now this, now this. This is not going to work in the world of robotics. It has to simultaneously happen. So many motors have to move like this while this is tilting like this with a very smooth motion. So that is what these motors are supposed to do. And how can you do it right? Through understanding of the right kinematics, through proper calculation and designing. Designing involves a lot of things here. What is the timing? Should this, while this robot is starting to pick the cup, should this tilt start? The answer is no. It should start after a certain delay of maybe 3 seconds by the time the robot would have reached here, right? If the delay is not there, it's going to spill the coffee or the tea over in the initial position as well, right? Like that's problematic. That's something I do not need. So what is the right amount of coordination between the different steps and the right motor movements, when one motor should rotate, when the motor should stop, when two motors should parallelly rotate, or when maybe 3 motors should parallelly rotate, what is the overlap, what is the outlier? These all things have to be well decided in advance in order to create a robot which has seamless types of movements. Hopefully this part is clear, right? There are a lot of transformations which happen, like for example, motor coordinates to joint coordinates. What does this mean overall? So my goal here is I'm supposed to bring my cup here, right? So the overall, if you look at the displacement, it is just this, right? But the cup will never be brought like this. There is a certain way of trajectory through which this is brought. What are the joint coordinates in order to create these kind of motions? You need to apply Pythagoras theorem, like many other equations of motions in certain areas. What speed do you take it? Newton's laws, right? What speed, what acceleration? V equal to U plus AT. These kind of things you have to use, right? So all those three laws of, Newton's and like other things, you need to make sure that by the time the speed has reached to a certain point, you are able to make other joint motions. So one motor may have to rotate slowly while the other motor is moving very, very fast. So simple relations with some mathematical difficulties will be experienced. What are some of the basic joints? These are the kind of joints which you are going to see. Revolute joints, which is 1 degree of freedom, right? Then prismatic joints, when one system goes through another, right? Just 1 second. Yeah. Okay. So revolute joint is, what are you seeing here? You're seeing some joints which are just going to rotate. While one joint is rotating, the other joint can rotate parallelly. Prismatic joint is one is coming through another. This is similar to a linear actuator. Then there are spherical joints with 3 degrees of freedom with rotations typically along different directions. So you can well see in the first one, the rotations are just within a certain plane. It cannot rotate out of the plane. So these are some types of basic joints which you will encounter in majority of the robots, right? So there are a lot of aspects which you have. There is a forward kinematics, there is an inverse kinematics. Typically, you have Cartesian coordinates which are there, then you have joint coordinates. What does this mean? So let's talk about this. What is forward kinematics? When you have certain joint motions which are desirable, like let's say I desire that my cup is rotated by this, so this involves certain joint motions, right? So I have to convert these joint coordinates to Cartesian coordinates. Overall, I want to understand where is the cup. This is all fine. I did some local joint motion, but where is the cup being brought? With respect to a certain position, it could be the stationary mouth, maybe. That is known as forward kinematics. Inverse kinematics is when I know my final destination is bringing the cup to the mouth, and I find out the joint coordinates to figure out that how much this rotation should be there, how much that rotation should be there. 3 joints needs to rotate by how much in order to create this final motion, which is bringing it through this much amount of displacement. Hopefully these aspects are clear. What is forward and inverse kinematics? Forward is joint coordinates to Cartesian coordinates, and inverse kinematics is Cartesian coordinates to joint coordinates. You have to use matrix transformation equations to do that. I'm sure many have taken a course in basic mathematics, vector geometries, like where you have large matrix, you have transformation matrix, which are used to look at what if there is a rotation, what happens. Okay. So we are interested in 2 kinematics topics, which are there typically in majority of the robotics work. One is, like I said, is forward kinematics, like or kinematics, which is focused on how to create angles to position. So your inputs are length of each link, the angle of each joint. And the goal is, can you find out the position of any point? It's XYZ coordinate with respect to a defined origin. That is the goal, right? So length of each joint. So let's say this is my arm, length of this arm, length of this arm, this part of the arm, angle between the two. This is what I have right now. But due to this stationary position, where exactly is my final tip of my arm, or maybe the tip of the cup while I'm holding this arm like this, is positioned with respect to the mouth. This is the final outcome which is needed. Right? Hopefully this aspect is clear. So the end goal of a robot is to meet the final solution. So if the robot is supposed to get me the cup so that I can sip my tea, that is what it has to do. Whatever the joint motions are happening from an outsider standpoint or a customer standpoint, that is not important or not relevant. That is relevant from a designer standpoint. I have to know as a robotics engineer that how the design should be done so that it is able to do this particular operation. Right? So from a designer standpoint, I need to know what is the final position of my solution while I have designed all these linkages and angles and their rotations. That is known as forward kinematics, where I can convert angles to position and figure out, have I been able to reach the final position where I was determined to reach or not. Inverse kinematics is just the reverse, right? You are going from position to angles. Here, the problem statement which is given is, right now the cup is here. It is told that whatever you do, we do not care. It has to happen like this cup has to reach to my mouth, like, and it has to tilt like this. This is the final destination. Due to this, please design what kind of rotations are needed in each one of these motors. This is when you need inverse kinematics. Because unless you know what each of these motors are supposed to do and by how much, you will not be able to design your robotic systems. Because that is the software coding also which you are going to do with these motors, that have a delay of this much, then start, have a 1/5 of a revolution and then stop while the other motor starts. And this is going to, let's say, finally bring my cup here and proper tilted. All I have to do and sip my tea. I'm taking this example because this is easy to show with the hand gestures, right? So hopefully the forward kinematics and inverse kinematics is easy to understand. Inverse kinematics is, which is very important from a designer standpoint, that this is my final goal. How do I accomplish that goal? Through the designing of the motors and how much they should rotate, how much they should translate. So inverse kinematics is important for the designers. Forward kinematics is important for the customers typically. Because here you have converted as a designer the angles to the final position. So the customer would not want to know about the angles. They want to know what is the position. Customer is not always like people like us. Customers could be a defense personnel. It could be a person who is purchasing the robot for putting it in a factory or doing certain assemblies and things like that, right? So knowing the final positions is very important to them. They do not care what angles things are in. So hopefully the forward and inverse kinematics is very important. Forward kinematics is for the customers, inverse kinematics is for the designers. Okay, let's look at the description of the mechanism. The mechanical arrangement of a robot, let's assume, is like this on the left, right? So if you want to determine the position of a certain component to figure out your robot design parameters or your coding, how things should move, what you have to focus on is all the linkages and their orientations. Your focus should not be in all those small little linkages which are not moving. You have to only focus on the moving joints and the moving linkages, right? So in this particular case, this entire picture has been replaced with these 3 linkages which may have motions in certain direction, right? So one linkage at the bottom, one at the top, one on the side. So it could be so that the top linkage is rotating with respect to the bottom linkage. The one on the side is probably translating with respect to the top linkage. Right? So this is how you have to convert your robotics problem, which might be a very sophisticated problem to work on, into simple linkage based problems. Then only you will be able to define the kinematics. Otherwise, it's a crazy thing to work on, right? Okay. Next, let's talk about the kinematic chain, right? So there is something which is known as the open chain, then there is something which is known as a closed chain. What is an open chain? Open chain is where you have a serial mechanism. So many of the robots, many of the machines, including the robotic arm, what you will see them, they serially do things. So one thing at a time, one after another. So the first step is probably you move the arm like this. Second is you twist the arm like this, you bring it close. These are all separate steps. This is known as an open chain kinematic problem. Typically for good dexterity, high flexibility, large working space, good accessibility, this is all good. But majority of the humanoids and advanced robots have closed chain mechanisms, which are parallel mechanisms, to make sure that 2 or 3 mechanisms can run in parallel. Right? While this is happening, this is quickly done through a seamless step of motions. And this is typically a compact design, high accuracy, high stiffness, and high payload, right? Majorly, these are the systems which need parallel mechanisms. High payload means you are trying to lift some bulky equipment, bulky parts. There you need to run certain motors together in parallel in order to execute that task. It is not that simple and straightforward that you just run a few operations one after another and it will work. So open chain and closed chain kinematic chains exist, right? Constraints of the kinematic chain is very important. The positioning accuracy decreases with the number of axles. Each additional axle means additional cost, right? Like this is an example from automotive. So engine, transmission, brake, measuring system, storage power, amplifier. The carrying capacity is reduced with increasing number of axles, right? Like so. This is one of the examples where you can have certain constraints to the kinematic chain. The more number of constraints you have, the positional accuracy decreases. These are some dominant kinematic chain. The first ones are based out of arrangements. Just look at it. The first picture which you see under the arrangement, this is quite familiar. You could see this in places like a 3D printer, right? To some extent, or a cutting machine to some extent, but these are just focused on arrangement. The other ones have a telescopic kind of a system, which are like what you see in the robotic arms, right? There are several other kinds of robots like the KUKA robot and many others like which are falling into this arrangement kind of dominant kinematic chains. Dominant kinematic chain is your robot may have a lot of operations, but what is the dominant operation, or the more important operation which is dominating the other operations, right? The substitute images for all these operations is as simple as what you see in the second row. These are some linkages with certain definitions which clearly states. So if you see one link in between another, which is kind of sandwiched in between, that typically states that the link is able to telescopically come in and out. These are some standard symbols which are used. If you see certain places where a cylinder is placed, they may be completely constrained or they may be okay to go for a rotation, right? So there are certain constraints which needs to be placed, but typically all these complex arrangements can be broken down into some simple steps of linkages and how things can move. Next is from a working space standpoint. In all these arrangements, what you see is the first one goes within a large volume. That's why this is applicable to the 3D printers, cutting machines. Here you can go in X, Y, and Z. It is all workable within a volume. By workable within a volume, I mean, if I was to put this cup in the arrangement 1, it is able to traverse through this entire volume and go anywhere where it likes. If I was to place this cup on the second arrangement, it will only be able to do this, which is like rotate on an axis, not translate, right? If I go for the third arrangement, it may be able to rotate and rotate in different directions, right? These kind of things may be allowed. If you keep on going in certain arrangements, it may be able to do rotation and translation both. Yeah, Joydeep has a quick question. Shouldn't the weight of the cup be considered? Yes, it has to be considered. It has to be considered, yes. But when you're looking at kinematics, you don't have to think of it, because if you're designing a robot, it should be able to grasp the cup without affecting any of its mechanisms. Means without affecting any of its linear actuation systems or rotational actuation systems. If it is able to grab the cup well, without any kind of loading which is affecting the systems, it is fine. You can do without thinking about the cup's weight. Even if you give a larger cup or a cup with a higher weight, it should be just doing okay. Hopefully this makes sense, right? So irrespective of the forces which are acting on the robot, it should be able to at least have a range of things which it is. The payload will come later. Yes, that will come later. That's the right point. Whenever you have a higher payload, then you need certain robotic mechanisms. Probably you need a higher torque or higher amount of forces which the motors can apply in order to work with such payloads, right? So typically, if we are looking at robots which are supposed to lift very heavy objects, we are looking at motors with extremely high torques. The speed will of course get compromised to a certain extent, but the torque should be high. Or in certain cases, in linear actuation systems, the amount of force delivery which it can do should be higher, right? That is where the system of payloads come in. So typically the robots come in for certain functioning. So let's say the purpose, if it is just to pick a cup, you just benchmark it against all sort of cups which are available around the world. Let's say if the weight cannot exceed 500 grams or a kilogram, you design your robots accordingly. Your motor mechanisms should be able to not be affected by the 1 or 2 kilograms with some factor of safety, right? Then you do not have to think about what amount of forces this cup is, placing on the particular robot. So it is irrespective of the cup weight, irrespective of the cup's design, these robots will be able to perform fine. Once the payload increases, you need to design a robot specific to that payload. Hopefully this component is clear. So dominant kinematic chains are not focused on the forces. They're just focused on the types of motions which they need to accomplish. Right? Let's look further. There are lots of robots which are made with redundant mechanisms, sometimes due to an over design, right? So they could sometimes lead to a high flexibility of movements, but several combinations of the mechanism which can lead to the same outcome is more of a redundant mechanism. So typically what is known as all the robots with more than 6 axles or 6 arms. So if you have a 6-arm robot, right, like one arm connected to another in tandem, right, that is not of much use. All you could do that with like 3 or 4 arms, that should give you all the ranges of the motions, right? So anything beyond 6 is not necessary. It's more of a redundant system. That is what is being told. Yeah, so there's a quick pointer. In a redundant system with 7 degrees of freedom, if any one of the intermediate joints become locked, even though it only contributes 1 DOF, it will still affect the overall system, right? Even if the still a 6. Yes, you are right, Srivatsan. You are very right. Redundant mechanisms, we call a mechanism as a redundant where all the mechanisms are able to get all the degrees of freedom. And then also we are placing so many mechanisms. But if you are constraining the degrees of freedom, like 1 or 2 is constrained to only 1 degree of freedom or 2 degrees of freedom, then you will have to have more arms and more mechanisms which are in place. So what is being said here is, whenever you have access to high degree of freedom for each one of these linkages, it is better not to go beyond 6 linkages. Hopefully this part is clear. Hyper redundant mechanisms are still in practice. Many of us tend to over design robots, but it's not going to add much value, right? So this is one thumb rule to be just kept in mind. Let's look further. Okay, representation of the orientation. So you have to write down a matrix which will basically hold the different positional points or the initial angles which are part of the matrix. So elements of the matrix R are not independent, meaning like many of these values are dependent on each other. In total, there are 9 elements. All are orthogonal and have uniform length because these 6 terms are only 3 redundant with the matrix size. So representation of the orientation with independent variables can be in terms of Eulerian angles or Eulerian angles, like which is phi, theta, and psi, right? which are focused on the three kinds of rotation, which are known as yaw, pitch, and roll angles. Or you could have four independent variables where how much they are moving in each one of these directions can be shown. These are typically the Eulerian angles, right? Like everybody understands that anything can rotate like this or this or that, right? So these kind of three rotations are possible. So let's not get into the math part too much, right? Like, because I think that can be a constraint for many of us who have been in the industry for a while. But this is what you should know. Just look at this plane or the flight diagram. You should at least know what is what. So pitch is when your entire aircraft can go like this. So the aircraft is flying like this when it can nosedive or go up, right? That is pitch. Where it rolls from side to side, like, it is known as rolling. When it rolls like this, what is yaw? Yaw is whenever it goes from one left to right or right to left, right? That is known as yaw. So these are the three kinds of rotations which are possible with every joint of your robot, every linkage of your robot, if it is not constrained in all the directions, right? So yeah, let's look a little bit into the kinematic math just for the sake of it. I'm going to just quickly skim through these slides just in the interest of time so that we do not focus a lot on this. And I want to specifically focus on the human gait analysis because there is a lot to be learned from there which can be applicable to the humanoid motions and the different robotic motions. So let's just quickly skim through some of the kinematic math, right? So everybody knows what a dot product is most likely. If you do a quick refresher, you will know. So basically, if you put two vectors to a dot product, it is given by scalar of A, which is magnitude of A, magnitude of B, cosine of theta, right? So dot product is given like this. Unit vector is something which has a magnitude of 1. So it is basically the magnitude of the vector. So the entire vector divided by the magnitude. So that is this. Matrix multiplication is done like this. This is a quick refresher. So if you have a matrix like A, B, C, D, E, F, G, H, it's A times E plus B times G, right? Like that is how typically the matrix multiplication and additions are quite straightforward. A, B, C, D, E, F, G, H straight on added point wise, right? So these are quite important when you are running all the mathematical calculations from a designer standpoint for a robot, right? You need to do all these matrix multiplications, additions, transformations, which are basically mix and match of multiplications and things like that, right? Okay, let's look at this. So there are some basic transformations which are such as moving between coordinate frames, right? Like let's assume there are two different coordinate systems you want to so what is coordinate system? So let's say I'm looking at this cup. So depending on your reference system, you might be looking at this cup from different places. I might be looking at this cup from my wrist joint. I might be looking at this cup from my elbow joint. It depends. Let's assume this is the problem. Let's assume Vn, V0, which is the one in blue on the top right, that is the position of my cup, right? Let's assume I'm looking at the X and Y, which you're seeing, that axis, that is my looking from the elbow at the cup, right? That is my origin looking from the elbow at the cup. We are just thinking planar for now, right? So if I had to put a vector through from my elbow point all the way up to the cup, this will turn out to be something like Vxy, this longish vector. Now let's say I want to observe from the wrist. If I look from the wrist, that gives me a different vector because the position of the origin, which is the local coordinate system at the wrist, is quite different from what I saw in the local coordinate system from the elbow, right? So what I have here is I'm looking at the same point, which is where my cup is held. This is given by V and O, where O is your basically one of the directions and N is the other direction. This is the other coordinate system. So typically what do we have? If I add vectorially a vector Px plus Vno, it will give me Vxy. right? So I can do vector addition, vector subtraction to find out what is VNO if I know what is VXY, and vice versa. So think of this as almost like a reverse or a forward kinematics. Yeah, you have a quick question? Yeah, if not, I would request you to please mute yourself. So hopefully this part is clear. Where are we looking from? That is very important. And this is basically the basis of all your forward and reverse kinematics. Forward kinematics, what are we doing? We are looking from a customer standpoint, from angles we want to find positions, right? So let's say I'm looking from a certain position, like I want to find another position. That is what I can find out through this, right? Let's look further. Further, you can do all this math to basically figure out what is VNO, what is VXY, right, in terms of vector additions and whatnot. Okay, so what if there is translation along the x-axis and y-axis, right? What happens in that case? If one part is translating with respect to another, and we are looking at different coordinate systems, let's say this arm length increases, then what happens? We're looking at the same point, which is the cup. You will have a vector coming from the elbow, you will have a vector coming from the wrist, right? So again, that vector mathematics will hold place. So there are n number of ways to represent vectors. You can have them as a multiplication of a magnitude and a unit vector, or you can have additions, subtractions, and in certain cases dot products. I'm not going to get into all those details, right? Like, so because that can really take forever if I start getting into the refresher of math. But long story short, what you need to do is focus your attention on this, like where are you exactly trying to look from and calculate the position. If you know one position from the elbow to the cup, if you're trying to figure out the position from the wrist to the cup, this is how you find out, right? Okay, now what happens when there is rotation along a certain axis? Again, with rotation, you have certain vectors which happens. So what if this was the initial position of the cup? So basically I had my vector figured out from my elbow to the cup. I had my vector figured out from the wrist to the cup. And all of a sudden my elbow rotates by this, right? Then the position changes. So I have to take care of that rotation. Wherever that vector system is, I'll have to probably do more operations than what I had been doing just for translation. Right? So these are all vectorial rotations, vectorial translations, which you need to calculate using the vectorial geometrical math, dot products, cross products, vectorial addition, matrix multiplication, transformation matrices. Through this, you will be able to find out the rotation from the positions from the rotations, and so forth, right? Right. So this is some set of equations where this cosine of theta and all these things are being worked out. I'm not going to get into all those details because it may not work out for many of you. So typically, in other words, knowing the coordinates of a point in some coordinate frame, which is an NO coordinate frame, it's not no-yes type of thing, it's a coordinate frame system. You can find the position of that point relative to your original coordinate frame x0, y0 very easily, right? That is quite clear. And it could be so that both are local coordinate systems. Both my wrist joint and my elbow joint could be local coordinate system. My actual coordinate system might be somewhere in my room, from which I'm trying to calculate the final position of the cup. It totally depends, whatever your problem statement is. So you may be able to find out another vector, which is addition of certain other vectors. So using vectorial math, you'll be able to find all these coordinate system, irrespective of whichever coordinate frame of reference you're trying to pick from the very beginning. Then there are a lot of things like homogeneous representation. I'm just going to quickly skip through this math, right? And jump to the next part. So hopefully this part is clear. How do we find out positions based on the angles and angles based on the positions? Also, if certain positions are with respect to certain frame, how to find the position with respect to another frame? This is going to be the fundamental for all your calculations. If the customer asks you, how quickly can the cup reach your mouth? How can you figure this out? Right? You have to know what are the key motions which are needed, how quickly your motors can rotate and coordinate. Based on that, you can give a number to the customer. Right? Yeah, so there's a quick pointer. So we will have to essentially create packages that are unique to our model in Python and C++, and use in ROS to interact with the hardware. Are there any packages? Yeah, there are several packages, and you're right in saying that ROS is one of the ways of designing the robots very seamlessly and using a GUI. So just hold on for a few more lectures, and we will be introducing you solely to ROS and all these other Arduino based programming systems, and then you will see how you can do all these attributes even using ROS and even using Arduino programming, right? So all these things will be explained to you. So just request your patience. In a few more weeks, we'll be leading to that, right? But you're correct in saying that there has to be specifically designed packages in which you can create your code snippets, and they can be modulated in certain ways based on the operations, right? Okay, let's look next that now that we know that what is the math behind it, why do we need to understand the human gait? And why kinematics of the human gait is so much important? That is because we have one of the key goals in our life with everybody around the world trying to chase it, which is humanoid robots. Another piece of information I would like to share with all of you is very recently, just a week back, we have been getting a lot of funding push where a lot of companies, big companies like the Tata Consultancy Service, like TCS, government agencies are trying to build humanoids. Nobody has any idea how to build it, but everybody wants to build a humanoid. So that clearly states that the world is building humanoids so fast. And if you probably remember from my lecture on the market and what is the state of the art going into the market, humanoids is the next step of defense systems which are completely going to transform the borders. So Indian government has now, after a very lot of sleep, has like finally realized, like, and many companies have realized that we need to develop humanoids, right? So that's why kinematics of the human gait is very, very important to understand. A lot of funding is going to get poured into the humanoid research. So anybody interested in the startups and learning about how to build humanoids, we should understand the human gait, right? This is just a snapshot. So Harsh, can we take a 2-minute breather before we get into gait? Yeah, sure, we can do that. Yeah, totally. So I just wanted to finish this slide before we jump into the human gait, because it will take a while to really, and I would like everybody's attention for that, right? Yeah, you're welcome. So let's just look at this slide for a moment. I'll finish off with this one. So these are the humanoid robots which were just built in 2024. And this data I've picked up around June or July of 2024, a little earlier than that, maybe around May or June, I would think. So this is not even half the year gone in 2024. And you had so many state-of-the-art humanoids which were developed all around the world. While many of the countries are still sleeping, and now they have woken up like after a while, and they realize that we need to build something, and now they are looking for experts to build something. So what has happened in 2024? You're looking at HD Atlas. So if you're into robotics, you are a robotic enthusiast, you would know what Boston Dynamics is, right? Boston Dynamics is one of the very innovative companies which had built Atlas a while back, like around 10, 12 years back, where we had humanoids and similar looking systems, like which are as good as like any of the other systems which are built today, right? So Boston Dynamics is leading the way. This is from the US. There are Neo, GR1, Figure, Phoenix, Apollo, again another Atlas from Boston Dynamics. Then you have H1, Optimus Gen 2, right? What are some of the common things which you observe here? Things to observe within just a few months. What has happened here? If you look at the heights of these humanoids, they are almost like the humans, right? So gone are those days where robots are supposed to be scary looking. Right now, for the advanced defense systems and for around the world, they're trying to build humanoids which are human looking and with the human morphology or human attributes. If you look at the weights also, they're quite comparable to any human weight. 60 kilograms, 70 kilograms, 80 kilograms. And the third thing to observe is most of these humanoids are getting developed where? Either in the US, Canada, China. These are the countries which are leading the humanoid development circle. And before we know that, it could be the next missile thing, like which everybody is just sitting tight and waiting for somebody to come and change the things, while the other countries have an army of humanoids waiting to fight the wars. Right? So I'm just going to stop here for a moment and give you a 1 or 2 minute break, so that that has been requested. So then we start with the gate analysis. Right? Yeah, actually none from India. Something is happening at DRDO. I know that from my personal information because I visited DRDO. It's highly confidential. Typically, it's done below the DRDO. So you will never see on the ground. It's below the ground. So they're doing some things but still there is a lot of work which needs to be done. That's to answer Ganesh, right? So let's take a 1 or 2 minute break, really quick break. I'll also just take a quick bio break and we start with gate analysis, right? Where I would like undivided attention, right? So let's take a 2 minute break. Okay, so coming back, so I'm hoping everybody was able to take a quick break. So we now will be switching the gears into a very important topic, which is to understand the gate. So before we jump into the gate, I just wanted to spend 30 seconds on telling you why gate is very important. Because looking at these humanoids, of course, I've told you that that is the new era of robotics where these humanoids are getting built. Building them itself is a very complex task. And second part is you use AI, machine learning, and other techniques to train them. So one of the most complex tasks for these humanoids, if you look at, is the balance and the walking. So that's the bottom part of the body. If you're able to create that right, the top part you can design in any form or shape. It's just like a robotic set of robotic arms, right? Like which are there on two sides. But how the robot is going to get balanced is, will it be able to walk or run beyond the capacity of a human? These things are all decided by the gait. So at least it needs to comply with the human normal walking gait in order to futuristically build ways and means to be much more superior than the humans. So that's why understanding the gait analysis is very, very right. So with that note, let's jump into gait analysis. Okay, so what is gait analysis? Hopefully everybody can hear me and see my slides fine, right? So I would request everybody's attention on this gait analysis, which is very important. So it's a study of human locomotion dealing with walking and running, where irrespective of whether it's walking or running, it's a series of gait cycles. A single gait cycle is, yeah, just 1 second, is the math forward and inverse kinematics with software systems used to design robots do this? We need to know it intricately. Where can we do? No, so Prashant, I think it's a good question which he has asked. So forward and inverse kinematics, most of the softwares will take care of it. You know, so yeah, I will come to the Swadesh's question like next. So most of the softwares will take care of it. Do you need to study it in very much detail? Yes, you can study it in detail if you're going into the crux of building a very key robot which doesn't have normal kinematics or things in place. But typically most of the software should do it. It is more of a GUI system based rather than having you to code too much. So that's to answer your question. You do not need to study it very intricately these days like it was back in the day. Right. Next is Swadesh. Why is the focus so much on humanoids when balancing on the 2 feet is more difficult compared to, let's say, a dog for, say, a military system? So this is again a very good question by Swadesh. So the focus is on humanoids because of 2 or 3 key reasons. One is they are trying to create, like I said, defense systems where, the enemy may not be able to understand whether a human is coming or a humanoid is coming. Of course, right now with these pictures, you can clearly tell it's a robot, right? But right now, the innovation is happening in that area that even if you stare at certain humanoids, you will not be able to understand whether they are normal humans or humanoids. There are n number of such humanoids which are getting developed. So it gives a matter of stealth. It gives a matter of deception where somebody is not able to understand whether it's a human system or a defense system. So that's number one, why the focus is on humanoids. Second, focus on the humanoid is irrespective of defense. In many of the applications, like where you have hospitality industry, like security industry, where you need to deploy certain, robots which are going to work collaboratively with the humans. There, I think the matter of empathy has come into the system of robotics where somebody can relate well with typically systems which look like the humans. Yeah, so it is difficult to compare these points with a dog, which has some very different applications. So if you're looking at the dog-based robots, they are also used for defense applications, but majority of their things are focused on high speed. If a robot can run like very fast, go get into nooks and crannies where they can basically visualize certain things, collect information, come back. So those are the main attributes. Of course, dogs cannot fight like the humanoids can do. So think of the movies like Terminator and Universal Soldier. If any of you have watched those movies, so think about when Rob Van Dam, I think, was on Universal Soldier. He was almost like even though he was not a humanoid, he was a soldier, but like think of a humanoid looking like that, who is full pumped up energy, which is able to fight. So that is where there is so much focus on humanoids, and this is all around the world. This is, you look up in the news, it's all on the news, everybody is trying to pull it back. So that is to quickly answer your question, Swadesh. Our world is primarily designed or rather been designed by humans to be, so humanoids make sense. Yeah. So humanoids have a lot of reasons why they're like that. And if you look at the weight, heights and everything, why is it not height of 7 meters? Let's say 7 meters, like, or 7 feet or 8 feet, right? Why it's the humanoid not very gigantic? So that it looks like the humans. You know, so earlier, if you remember the history of robotics, while I was speaking about it, the goal was the man creates robot and robot kills the man. If you remember these sentences, like from the plays and where robots were looked upon. So that is kind of reflected in the initial movies like the Terminators and all that. What happens in a Terminator movie? Typically, the entire movie is a chase movie where the robot is running behind a human trying to kill it. That was the idea of the robots in back in the 70s, 80s, and early 90s. Over the time, the thing has shifted that robots can work together with the humans, and they need to be looking somewhat like the humans so that you can feel like you are in a safety zone, right? They're not going to do something, just probably twist your arm or do something where it can break your arm, right? So that's where humanoids make a lot of sense. Yeah, so if you, I think there are some points, if you do fix an autonomous targeting and firing shooting system, and then warfare is not limited only to bipeds. Yeah, this is true. There could be so many other kinds of warfare based systems which are getting developed. A lot of things are happening in India also. Please follow some of the startups. Many of the startups are getting into defense systems, right? Like, so very recently I have signed up with the Indian Army for some of these startups which are building some of the robotic technologies. Many of them are stealth technologies, which is very confidential. But these are coming more and more into the picture. The Army, Air Force, everybody is super interested in getting into robotics. Typically, the skilled manpower in robotics, they're trying to harness, right? So humanoid can also be used as substitute for dangerous jobs. Yeah, this I've already mentioned. So firefighter, astronaut, bomb disposal, right? Like there are so many chemical factories. Those are the places you do not want exposure to humans, right? Like, so for example, welding, these kind of jobs can be replaced by robotic machines or humanoids for that reason. And they have already done this in China as we speak. It depends on the usage. So with respect to 2 legs, 4 legs, 2 wheels, 4 and 6 wheels, yeah, it depends, of course. But majority of the humanoids, like I said, are not on the wheels. They are trying to replicate all the human motions, because human motions have a very specific way of motion which allows us to climb hills, you know, to have certain tractions on our body, like while we are going up the hill, down the hill, you know, we are walking in different terrains which cannot be found out through wheel-based systems. So that's why understanding the gait is very important. Is it also because of accessibility? I think Harsh's question might be related to the dog question, what I can relate with. I think if it is that, then yeah, that is related to the accessibility. Yeah. Yeah, because various joints are very flexible. Yeah, that is true. Yeah, many of the animal-based robots are created because of the accessibility. So there are robots which are, you know, micro robots, a small size of robots, which are also deployed in the human body because they can get into the nooks and crannies and basically look at visualization of the organs where there is an ulcer and whatnot. So there are so many applications which are just unfurling as we speak, right? So I'm just going to take a quick break from the chat meeting so you can post your thoughts. I'll look at it a little while later as we speak about gait analysis, because I want to make sure that I have full attention for gait analysis, right? All right. So gait analysis, like I said, is focused on the study of human locomotion, walking and running. Walking is a series of gait cycles. So a single gait is known as a stride. So while we walk or while we run, we are repeating the gait cycles again and again. So it's a series of gait cycles which we take. A single gait cycle is known as a stride. Okay. What are the main tasks of the gait cycle? The main tasks of the gait cycle are as follows. The first one is known as weight acceptance. These are the tasks, broad tasks. Weight acceptance is the most demanding task in the gait cycle. It involves the transfer of body weight onto a limb that has just finished swinging forward and has an unstable alignment. Right? So typically we may not be observant of how we walk because this is so normal or natural to us. But if you do observe how you walk, how you place your foot in the front, typically there is a heel strike. And while this heel strike is happening, the foot was initially off the ground, it was swinging, and then it created this heel strike. And it is supposed to balance the weight, make sure that there is a forward motion which is keeping on happening, otherwise you will not be able to walk forward. And it is also able to take the shock absorption, and overall progression is maintained. So weight acceptance when your foot first hits the ground, either of your foot, that is a very challenging task, right? How do you translate this information to the robots? By analyzing how the humans walk. Next is single limb support, where one limb must support the entire body weight. So there are places in your gait cycle where you are about to take your toe off. You are basically in the mid stance, which is stance is more of the entire part of your gait cycle when your foot is touching the ground. So during this time frame, you're about to take your toe off in a while. So during this time, one foot is supporting the entire body weight. The other foot is still swinging before it hits the heel strike, right? So think about a static position as if somebody took a snapshot while you're walking and you're on single foot. While you're on single foot, you're managing the weight of your body and you're about to take the toe off. So it is a very fine balance. And as you're doing that, you are also maintaining the forward progression of your body. So the single limb support is the next main task of the gait cycle. So here the same limb must provide truncal stability while bodily progression is continued. The third one is known as limb advancement. So limb advancements requires foot clearance from the floor, right? So foot clearance for the floor is needed. So you cannot be just doing left, right, left in the same place like you do in a school drill. You have to progress forward. In order to progress forward, you need a clearance between the 2 feet, right? Then only you can have forward motion. So the limb swings through 3 positions as it travels to the destination in the front of the body, right? So think about these are your 2 feet. One has to travel on the front of the body and the other has to travel next. Then only you can have the progression. So the main tasks of gait cycle are weight acceptance, single limb support, and limb advancement. These are the broad 3 tasks, right? Which the humanoid robot also needs to comply with. Then comes the next part, another broad attribute, normal walking requirements. Unless and until we know the baseline measurements or what are the normal walking requirements for the body in terms of kinematics and kinetics, we will not be able to translate the knowledge to the humanoid, right? So we need to take measurements from a lot of population who are walking normally. So there are 4 major criteria essential to walking. First one being equilibrium, which is the ability to assume an upright posture and maintain balance, right? So there needs to be a proper equilibrium between the 2 feet. Otherwise, if you look at humanoids like 20 years back, when somebody wanted to develop this gait system or translate the knowledge, most of them would fall forward or fall sideways. Or whenever they experience an obstacle, they will trip over, right? Maintaining the equilibrium while you walk is very, very important. Typically, when we hit a stone or hit a pebble, do we fall down? The answer is no. That is because we have an idea of like something is coming, that I'll come to that later, that comes through a vision system and things like that, that the robot may not know, but it should be able to overcome such obstacles, easy obstacles very easily, without having to fall down and restart from the location. So equilibrium is very important. Next is locomotion, the ability to initiate and maintain rhythmic stepping. So that means there is a coordination between certain motors which have to fire with the right time delays. If I fire a motor at the toe of my foot or close to the ankle of my foot first and later on till the around the hip joint of the humanoid, it's not going to work. They have to be done in a certain fashion, and certain things have to overlap, and there needs to be a certain parallel way of actuation which is in place, right? Which can be only taken through the human gauge cycle, right? So as these things are happening, musculoskeletal integrity is also important for the humans, which is the normal bone, joint, and muscle function. This is not applicable to the humanoids just yet, unless the humanoids also start incorporating muscles. Because what happens in the human body is a little different from the humanoids or the robots. In our human body, the skeletal system, which is all our bones, cannot do anything. It's just a skeleton. It doesn't have any power to do anything. So everything which is done is by the muscles. Our brain sends the signal to the muscles, they contract or they elongate in certain places, and they transfer these forces to the skeletal system to certain linkages, and those joints basically go like this and are able to basically conduct the different kinds of activities which we have, including the gait. This is not the case with robots. In robots, we do not have a muscle system which is getting a idea from the head and all that. It is straight on actuation, right? There are certain pre-coded things that after this needs to actuate this much, the motor needs to rotate by this much, or the linear motor needs to translate by this much. Or in case of AI machine learning based systems, you probably need to track an obstacle with a vision system. If the vision system states the obstacle is in your periphery, you ask the motors or dictate the motors should rotate reverse way in certain directions so that the robot can move away, right? So musculoskeletal integrity can come into the humanoids if these kind of systems are incorporated, but not just yet. The last part is neurological control, which is the humans must receive and send messages telling the body how and when to move, like visual, vestibular, auditory, sensory, motor input. These things are there in the robots and the humanoids as well. How? Through sensing systems. If you sense a pressure through a pressure sensor, you tell the humanoid or tell the robot to open up the fingers like this, let's say, through motor movements, rotation of motors or translation of motors, whatever is necessary in certain places, right? If there is a vision-based system, a camera system which detects there is an obstacle, that is similar to your sensory systems, right? So we humans sense through the different sensory organs, the robots sense through the different sensors. These sensor data is now taken and analyzed, and based on that, certain actuations are triggered, very similar to how we respond to any sensory systems. Like when I see something which is dangerous, I change my walking pattern. When I smell something which is dangerous with a smell-based sensor, you can do that with a robot. I do certain things which are different, right? When I get taste may not be very, very important, but like typically if I hear something different, some noise like of a train coming, I'll not cross the railway crossing. Similar to a robot, if it hears certain noises, this all depends on the kind of algorithms which you have in place, right? It can detect and at least be careful, right? So neurological control is important in humanoids and robots. Musculoskeletal integrity, not just yet. Equilibrium and locomotion are extremely important. So these are the normal walking requirements. So let's talk about the gait cycle or the stride. A single gait cycle or a stride is defined from period when the first foot contacts the ground to when the same foot contacts the ground again. This is the definition of a single gait cycle or a stride. So first when does my foot contact the ground? At the heel strike, and up to the next heel strike when it contacts the ground again. That is the entire gait cycle. Each stride or each gait cycle has two phases. One phase is known as the stance phase, which is when the foot is in contact with the ground, and the second phase is known as the swing phase, when foot is not in contact with the ground. Right? Hopefully these parts are clear. This is a very important figure which we should pay some attention to, right? So let's pay attention to the figure on the front foot, like, or the so this is left and right. Just think about the foot which is towards outside the screen. So the one which is left foot is inside the screen, the one which is right foot is outside the screen. So let's focus on maybe the foot which is outside the screen, the right foot. So what happens, there is this initial contact which is the heel strike. During this time, of course, you cannot be flying. The other foot is about to take off while you're doing the heel strike. So this is known as the first double support. And this is part of the initial contact. And these are all parts of your stance phase. So just focus on the right foot for now. Right foot goes through a heel strike. Now you have a loading response. Then it completely settles on the ground when the entire foot is in contact with the ground. This is known as mid stance. Terminal stance is when this same right foot is about to take off from the ground. Right? Then it starts the pre-swing, right? So just focus on this right foot here. Hopefully you can see my mouse. Right foot here, complete mid stance. Right foot here, about to take the toe off. This is the terminal stance when the toe is actually getting off. This is the right foot. Please tag the right foot. And it has started the pre-swing. Then comes the initial swing, mid-swing. When the foot is about, it has crossed the other foot which is completely on the ground. And it is taking a forward movement. And finally, the terminal swing when the swing is about to end. Right. So you hopefully can see the switch between the stance phase and the swing phase. During this time frame, there is this first double support. There is a single limb stance where one foot is completely swinging. The other foot is completely, the right foot, which is the foot of interest, is completely pushing on the ground. Right. And then you have a location of second double support when the right foot, which we are tracking, is about to take off and the other foot is about to strike the heel. They're just, other foot is just, there is a heel strike and this is about to take off. And there is a single instance or snapshot in which both the feet are basically balancing the load. So hopefully this part is clear. This is the stance phase, this is the swing phase. So each one of the foot like is basically going through this entire gait cycle. So the gait cycle is focused on one foot only. One foot when it strikes, conducts the heel strike for the very first time up till the entire stance is done, the entire swinging is done, and it is about to hit the ground again. That is known as a single gait cycle. This is very, very important, right? Hopefully this part is clear. This is another way of representation of the gait cycle. Like stride can be divided into stance and swing. Under stance, there is weight acceptance, there is single limb support. Under the weight acceptance, there is initial contact loading response. Single limb support, there is mid stance, terminal stance. Almost like there is a little bit of an overlap with pre-swing. Under the swing, what you have is limb advancement. Swing is focused on limb advancement, which is the stages like pre-swing, initial swing, mid-swing, and terminal swing. This is just another way of describing the previous figure. Okay. If you look at the joint motion and muscle activity during these different phases, what is of interest is the joint motions. What you see in the top is the stance phase, which is 60% of your gait cycle, and swing phase, which is 40% of your gait cycle. Something has been colored in black. One feet has been colored, or one side has been colored in black on the top, just to create a clear focus on where we should focus on. So heel strike on the black, then the stance phase starts, toe off on the black, finally the swing phase starts, and finally the swing phase is about to end with the next heel strike. What you see in between are the initial different conditions which are happening, right? What you see at the bottom are the different joints, how much they rotate, going from the hip to knee to ankle to subtalar joint, which are the different joints which are important. And these joints you will be making for your humanoid also, or any robot which can walk. These are very important joints. So whatever gait cycle you're trying to establish in, standard gait cycle, that has to be established through these joints and the motion of these joints, which how do you actuate? Using motors. So what are the things which are happening during the initial stance phase? You have a forward pelvic rotation of 5%. You have a hip flexion of 30%, 30 degrees, sorry. Subtalar supination of 5 degrees. These are just some terms, pronation, supination, right? What are the other kinds of joints? What are the joints doing in different other stages? These are very well established in literature. So in order to go from 5 to being in a constant state of 5 to going to 0, you know how much of rotation you need to go from 5 to 0 in a particular motor, which is exactly what this human joint is doing. Or to go for ankle plantar flexion from 0 to 15 degrees while the limb is supposed to advance, how to go from the 0 to 15 is a simple calculation. You see what is the speed of the motor, right? You divide it by the time, you get the rotations which happens, how much of rotation is causing that much of a angle change. So entire rotation is 180 degree, 15 by 180 will give you, sorry, entire rotation is 360 degree, 15 by 360 will typically give you how much of the rotation is needed, right? So hopefully this joint activity is quite clear during the gait cycle. Further into the stance phase or the gait phase, when the foot is in contact with the ground only, propulsion stance phase has 5 parts like initial contact, loading response, mid stance, terminal stance, and toe off. If you look at the pressure profile of the foot at the bottom, this is how the pressure profile looks like, right? Why is this important? Because this is how you need to move the humanoid or the robot pressure profile. The robot should not have a foot like this, which cannot move up and down. It should be able to go sidewise, up and down. Otherwise, it cannot simulate the gait cycle properly. Most of the previous age robots used to have just a iron setting, like with a leg which is fixed, which cannot move sidewise, up and down, or twist. So that's why establishing gait with a humanoid was very, very challenging. But now that with research, we have been able to understand how the humans actually walk. We have been able to establish that with the humans. I'll give you another example just to sideline yourself. Like many of us may ask ourselves, like, why is gait so important? This is so normal. What is the big deal? Think about basically a toddler who is trying to walk for the very first time. What is happening with the toddler? They're trying to basically shift their weights, balance themselves properly. And initially, when they're about to put their one step forward, they'll probably fall down. Slowly and steadily, through proper feedback, they're able to gauge that these are some range of motions. If I do them in the order, they are not going to work. I do not have the luxury of having a robot do that through AI and machine learning, trying thousands of combinations, learning like a toddler. I don't want to do that. So that's where we can save a lot of time learning what the normal gait motion of the humans are and translate the knowledge to the humans. Hopefully this makes sense why we cannot get away with just any leg or any kind of lower extremity for any robot which is supposed to walk like the humans. That's why understanding the gait is very important. So there are n number of other things which happens during the stance phase, which is when the foot is completely in attached to the ground or in touch with the ground. What all things happen? These are not in the lower extremity per se. The shoulder flexes. Shoulder flexes. Pelvis rotates right. This is what happens to the humans. Spine rotates left. Hip extends. Knee flexes. Ankle plantar flexes, dorsiflexes, and plantar flexes. Foot pronates and supinates. Toes flex, extend, and flex. What is the importance of all these things? These are all joints within your body. So what I mean to say from this slide is to create the right gait pattern in the humans or the humanoid. It is not only matter of the bottom part below the hip. It is a lot of motions of swinging the arms, how we flex our shoulders, how we move our spine, that we are able to move how we move, right? That's why humanoids need to also be designed around that part. So to establish a human-like gait, it is not only a task of the ankle or everything down the hip, it is a task of all the components, all the joints in the body, like even the shoulder joints, where then there needs to be motors which are basically rotating or applying torques in a certain way. Hopefully this part is clear. Right, so this just showcases some of the phases. I'm just going to skip over, right? Like some of these pictures are just a reiteration of what I've shown you in the gait cycle, right? So if any of these positions during the heel strike, while the foot is completely in touch with the ground, mid stance, terminal stance, when the foot is about to take off and things like that, pre-swing, swing, mid-swing, forward swing, terminal swing, all these positions, if you were to take a snapshot of this person, you can freeze the frame positions, you will see the shoulders, pelvis, hip, every joint is doing some different range of motions and by a certain degree angle, which as a whole in a coordinated system is causing the proper gait to happen or proper walking to happen. So just to re-emphasize, all these joints have to work together as much as possible to make sure that there is proper balance in the humanoid. It is able to propel, it is able to walk normally, at least, and not fall down with small obstacles like pebbles and things like that, right? Okay, so these are the different phases again reiterated, right? Mid stance, static positions at mid stance, terminal stance. I'm just going to quickly run through them in the interest of time. Static positions of toe off, right? Okay, another part during gait progression is the time. One is like how much torque you require in each one of these joints or the motors to ensure that there are actuations which makes your gait happen. What are the timing of these gaits? How the motors should work, when they should be activated, when they should be deactivated. Let's say there are 20-30 joint based motors which are there as a part of the humanoid, replicating or trying to replicate the human motions through all the joints. How do they go in tandem? How do they go in progression? While my other foot is progressing, do I put my arms up? Which ones need to be in progression? That all comes through coding, and that all comes through understanding of the human timelines, right? So if you look at the right heel contact, left toe off surface, left heel contact, right toe off surface, right heel contact, and all these things. If you look at right stance phase, right swing phase, you're looking at some double support regions, right? So these stance phases, swing phases are timed like this. One is for right leg, one is for left leg. It is also showing you the time-based overlaps. So if you do your coding, you know when the motors have to fire by how much, so that this proper gait, beautifully created gait of the human body can be executed, right? This again kind of reiterates the swing phase and how important it is. I'm just going to skip over these pictures, right? So this again has the swing phase. We are going through the entire gait cycle, which is focused on one foot. Again, you will see the joint movements in any static position, like mid-swing, shoulder is neutral, spine is neutral, pelvis is neutral, hip is neutral, knee is flexed 60 to 90 degrees. That gives a clear indication of how much the motors should rotate. Ankle is plantar flex to neutral, foot is neutral, toes are slightly extended, right? So these are some static positions, right? So this is to show you the gait analysis. Hopefully this part is clear. And that's all I had for the slides. It will be nice if I can take a few questions. I think there are some questions which were there. So hopefully this lectures have given you some insights into what kinetics is, what kinematics is, what area of work they come under, what is statics, what is dynamics, and how this kinematics is so important as a part of the robots, whether you're working with a two-legged robot, like, whether you're working with a robot which is just supposed to do certain tasks or is coming closer to the humanoids. We have also emphasized on the importance of humanoids in different application areas and why they're so important for defense applications. And in order to be building humanoids, you need to understand this gait cycle, how the human gait cycle works. And then you can probably to expedite these humanoids so that they can run like a cheetah, you can derive some of the gait cycle based information from the cheetah or from certain animals, like who are doing certain types of gaits and things like that to enhance those humanoids. But step one of building a humanoid is always focusing on how the humans do it, how they walk or how they move normally, replicating the same into the humanoids. So hopefully this lecture has given you some good insights into what is the math behind it and what is the way the gait cycle works, right? So I'll just quickly take some of the questions and then we can call it a day. It is also, so this was done. Would a small tail in humanoid provide balance? Archik has asked this. I don't know, actually. I don't have an answer for that, which is solid. It may. It depends on what kind of weighing mechanism or what kind of weight balance this entire humanoid has. In certain cases, if you look at some of these humanoids, the picture which I had shown before we took a 2-minute break, many of them had a little broader bottom and some of them had a narrower bottom. So I think they had very different ideologies of how to shift and balance the weight. So whether a tail would be universally helpful or not, I don't know. In few of these humanoids, they may be of use, right? Yeah. Okay, yeah, Ganesh has shared some very interesting articles. Humanoid robots stride into the future with world's first half marathon in China. So like I've already told you, thanks for sharing this. Just look up humanoids, you will see where the world is going, and all your knowledge of AI, machine learning, you are doing software coding, hardcore robotics, they are all going to be applied in humanoids. So if you're trying to work on the drone space and things like that, which are already cluttered, you may not find a lot of interesting projects, but this is where the interesting projects will come in. Because this is going to stay for a while. How to create a humanoid, that itself is a challenge, different parts of the humanoid. And second is, how do you make them super efficient, which is suitable for a defense application, right? So this is going to be really, really interesting. Next is Swadesh has a question. Would we consider pneumatic actuations close to human muscle movements? Yes and no. I think many of the electronic actuators can do the job quite well these days, given that there are a lot of torque and force possibilities. Pneumatic systems are sometimes difficult to manage in general, like as compared to some of the easily digital electronic systems. Can they come close to the human muscle movements? We'll have to try and test. It depends. Many of the electronic systems are also able to replicate some of those movements, using shape memory alloys and actuation systems like that. But this might be something worthy of consideration. So, yeah. Is gait cycle only applicable for walking and running or also for jumping? Good question again. So gait cycle typically by definition is only for walking and running, but it is highly applicable to running, all the different kinds of movements in the sports, like in the game of football or basketball, cutting, running, like all kinds of while you're moving or past somebody, like maneuvering, these things are getting more and more into the forefront. So this is what is the new age of research, and you have pointed very rightly. We understand the gait of walking very nicely, and even to some extent the gait of running, right? That is quite clear based on the speed of running. But what is not known is the gait which we see in sports, right? So this is the next line of research which is coming along. So if you want humanoids to play sports for you, you need to learn about the gait which the athletes or the sportsmen have. Like, so this is a good point. Those joint range of motions are common for any type of gait cycle, or is it for normal walk on flat surface? So this is typically for normal walk on the flat surface. This is again a good point, because if you're trying to walk up the hill, then you need to have certain surface textures or certain coatings on the bottom of the feet. So there is traction and the gait cycle has to change slightly. It is very similar to while you're trying to climb up the hill. Your gait will not be normal how you generally walk in a flat surface, right? So a lot of these things are open for research. Many of these things have happened typically in a gait analysis lab, where they have created terrains where they can test using a motion capture system, force platforms, understand the forces, understand the motions while somebody is trying to walk up a ramp, down a ramp, changing ramps, changing angles through the obstacles. So there are so many things which are coming more and more into it. So when I get to the lecture on humanoids later on, I will show you some very interesting videos from Boston Dynamics where they have perfected all these movements, right? Majority of the things which we are talking about, right? So Joydeep has a quick question. While the right black leg is stepping in, the left leg is also swinging, then why only one leg is considered? So the reason one leg is considered, because by the definition of gait cycle, it is focused on one leg. So it is not like one leg is considered for designing your robotics. For robots, both legs have to be considered, but they will be moving in a certain coordination. So just to understand the gait cycle for the humans, we have placed the figures like that. So it is not like both are not considered. Both have to be considered. Otherwise, a robot cannot walk on one leg, right? So that is well understood. So Swadesh has been climbing through the steps. I'm guessing additional measures on top of gait walking cycles to be considered. Yes, this I've already just answered. So this needs to be looked at, that what are the motor movements, just does more torque is needed, because typically when you climb up the hill, you need more force or more energy to climb up the hill. How do you have to change the angles or switch your body so that you do not fall down the hill and things like that. So that has to be done, right? So gait is required to when a humanoid fight with the leg in hand. Yeah. So this is another important part. Yes, gait is required. So it might be stepping back. Just think about a sport where it is a fighting based sport. Like think about boxing, for example. So what happens in boxing? Boxing doesn't happen like I just stand here and start punching, right? So there is a jumping movement, there is a maneuvering movement, right? So somebody keeps on locating through the sensory organs, like when which can be incorporated through a vision system, and constantly you're looking at where the punches are coming and you're shifting weights, right? So when a humanoid actually fights, these kind of things have to be put in, and you are right, this is the future of humanoid. So even though somebody has created humanoids to walk and do certain activities properly, but in order to fight effectively, those things are yet to be done in most of the countries. That is where the startups can come in. If time permits, can we get a video analysis where you can explain us the various stages of cycle using a video in the upcoming day? Yes, I will be doing that, maybe for humanoids or robots. This I already have in the planner, so I'll be explaining that in the coming days. Gait analysis is very, very interesting. Yeah, we typically do not think about our walking or the gait, but I start thinking about it a lot because I work with a lot of people with gait deformities who have had spinal cord injuries, accidents, and things like that. Just by looking at their gait and analyzing those things, you can tell that something is wrong. Even when you have got a hairline fracture or a ankle twist, the gait changes. So the gait is something which is quite different, like when some kind of an event happens, and through tracking of that, you might be able to predict what has gone wrong. So gait is a very interesting subject. So typically, if you look at the area of kinesiology and biomechanics, they are typically focused on gait. Can I share the syllabus copy? I think I've already shared the entire schedule, and it should be up on your LMS. So I would request Varun to just look into that. If it is not, I would request Times Pro to please assist. I think it should be on the LMS, right? Is there any software package for humanoid gait, and can we update a YAML file for our humanoid specifics like height, weight, etc., degree of movements? Yes, there are software packages. I would just hold off on that for a while you start designing your linkages and everything on ROS and Arduino based platforms. So just request you for some patience till there. Yes, there are software packages where you can clearly calculate that these are the linkages, these are the angles, how much they rotate, and where they finally reach. So all the forward and reverse kinematics, right? What about assignments and exam details? Yeah, so it is a relaxed system for now. The assignments will start coming up once we start the hands-on. So just stay tuned for the for the next few days once we have the project kickoff, and then we will start with the assignments, right? Can the rheological fluids replicate the walking in tissues in humans? So Philip, very interesting point. Please hold off your thoughts for a while. When I start talking about biorobotics, you will see a lot of fluid mechanics and other things which comes into things, that how some of the bio-inspired or biological things can be put into robotics. So I have some very interesting lectures which are lined up for you in the coming weeks or so, right? So just hold off on your thoughts on this, right, for a while. So many simulations already available. Is the gate still a problem, or the real problem is the adaptability of the robot based on the environmental changes? So yeah, Adam has put an important point. So simulations are already available, and many of the gate parameters are done right. But whenever you're designing a new humanoid, you're designing it with certain capabilities which are better than previous ones. So then the weights change, the kind of payloads change. There you need to recalculate these gate parameters again. So that is number one, where this still poses a challenge to make sure that the walking is normal. And second part is adaptability. If they're going in rough terrains, it has to be trained in those terrains, right? Like, or at least some simulations of those terrains through AI machine learning. Otherwise, they will not be able to perform any military operations or things like that, right? So China's Unitree to life Wallstream first humanoid robot boxing match. So I was just talking about it. That's why I use the words as we speak. A lot of things are changing. This is my common punchline, because actually as we speak, a lot of things are happening around the world. The first boxing match is happening in China with the humanoids, right? So it's worthy of a watch. So thanks for sharing this, Abhinav. Is it possible to undergo the gate analysis for yes, you can do a gate analysis for the humans and gate analysis for the robots also. We typically do it in any biomechanics research in a gate lab, right? Just look up gate lab and you will know there is a motion capture system with many cameras and a force platform which measures all your forces while you walk and all your motions, the accelerations, velocities, everything, right? So next is Prashant. I have a spinal disorder and so I walk with a stick. The entire gait analysis is usually fascinating to me. Can I read about it in more detail someplace? Yes, please look at gait-based disorders. If you're interested in certain books or text, we can probably provide you some good answers. So I typically work with the Indian Spinal Injury Center, which is ISIC in Delhi. They have a lot of rehabilitation. So rehabilitation means if you're walking with a stick or certain kinds of exercise which are supposed to be done, they keep on tracking whether this is deviating from your normal gait and how much is the deviation. Of course, if you have an injury, you will have deviations. So through this training, physiotherapy and all the physical exercise, can you decrease this deviation so that your gait can be rehabilitated to normal? So this is one of the interesting areas in rehabilitation, right? So yeah, you can read more about it. If you need a very specific textbook, I can probably, based on your requirement, give you some, right? You're a prosthetist. I'm doing research to develop new knee joint. Can you suggest some actuator I should look at? So just stay tuned for 1 or 2 more weeks where we will have lectures focused on actuators. So you will get a better idea on all those actuators, and you will know very well that what can go into the prosthesis, like, in terms of the knee joint, right? Which has multi degrees of freedom with certain constraints, right? Is the gait of each person truly unique? Yes and no. There are some unique possibilities due to multitude of reasons, like how your arch is and things like that. But typically there is a normal baseline with 5-10% deviation in which the average human gait can be characterized. So the answer overall is a no. It's not uniquely unique, right? Swadesh, can AI learning systems help robots with learning gait by observing training with respect to actuation parameters? Yes. This is the next stage of research where most of the defense systems and humanoid systems are focused on, right? That how can you, now that the robot can walk normally like the humans, how do you adapt to the gait? Of course, the capabilities have to be there with the actuation system also. If the motors have limited torque, it may not be able to do that gait in very difficult terrains, climbing up the hill. So they have to also be adapted, but AI machine learning can be used for that, right? So that hopefully answers your question and ends the lecture. So that's all for today. We are at 2:41. So I'm just going to have a hard cut off here. So hopefully all of you enjoyed and learned a lot about the gait analysis and how the humanoids work today. We look forward to seeing you all also in the next week. So just have a good weekend. Thank you, everybody, right, for today.
Thank you very much. Thanks a lot.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you,
Thank
Professor.
you. Bye.